Something is leaving our solar system right now. Tonight, as you close your eyes and let this voice carry you somewhere far from the noise and urgency of ordinary life. Something is out there in the dark, moving. Something that is not ours. Something that has never been ours. A traveler from another star, older than the sun, older than the Earth, older than almost anything we can name in the solar system. And it is sliding past Jupiter at 130,000 miles per hour, on its way back to the interstellar void it came from. Passed through our sky, briefly, silently, without asking permission. And it left us with more questions than the universe had previously allowed us to carry. Its name is 3I/Atlas, the third known interstellar object ever detected passing through our solar system. Discovered in the summer of 2025 by a telescope in Chile that was not even looking for it. Tracked by every major space instrument humanity has ever built. Photographed from the surface of Mars's orbit. Analyzed by the most powerful infrared telescope in existence. And now, as of this very moment in March of 2026, receding from us, fading from our instruments, carrying its secrets back into the dark between stars. This is the story of what we found, what we think it means, what it forced the scientific community to confront. Not just about the universe, but about ourselves and the profound limitations of what we can see, what we can reach, and how ready we are to answer the question that has haunted our species since the first human looked up at the night sky and wondered whether anything up there was looking back. Let's start not in space, but in the Atacama Desert of northern Chile. It is an extraordinary place, one of the driest spots on the surface of the Earth. The air is so thin and dry and cold that it behaves, in optical terms, almost like no atmosphere at all. The stars from the Atacama don't twinkle. They burn, steady and sharp, like headlights rather than candles, because there is so little water vapor and turbulence between your eyes and space. It is one of the reasons that a disproportionate share of the world's great telescopes are clustered there on those high volcanic plateaus. The European Southern Observatory's Very Large Telescope, the Atacama Large Millimeter Array, the future Vera Rubin Observatory, and dozens of others, all pointed at the sky because the sky from that place is as close to looking straight into space as you can get from the ground anywhere on Earth. In a valley in that desert called Rio Hurtado, a narrow, brown, sun-blasted fold in the Andean foothills, sits one component of a system called ATLAS. That stands for Asteroid Terrestrial Impact Last Alert System. It is not a glamorous name. It is not the kind of name that sounds like destiny. It is the kind of name that sounds like a municipal infrastructure project. Functional, purposeful, unglamorous. A piece of planetary defense hardware, funded by NASA, designed with one specific goal: to find things that might be heading toward Earth and sound the alarm before it is too late. The ATLAS network is not a single telescope. It is a constellation of them, spread across Hawaii, South Africa, Chile, and elsewhere, scanning the sky every night in overlapping arcs, looking for anything that moves, anything that doesn't belong, anything that wasn't there last night and is there now. Night after night after night, in an endless automated patrol, these machines watch. Because space is not empty. It is full of rocks. And some of those rocks have trajectories that intersect ours. On the night of July 1st, 2025, the ATLAS telescope in Rio Hurtado was doing what it always does. Sweeping, scanning, logging thousands of objects, filtering, comparing tonight's images against last night's images, flagging anything that moved. And somewhere in those comparisons, a flag went up. A dot, moving, magnitude 17.8, which is so faint that you would need a 12-inch telescope under perfect dark skies just to glimpse it as a pinprick of light. The human eye in the best conditions could not see it, but the automated system could. And what the system saw made it alert the astronomers. Within hours, not days, not weeks, but hours, the orbital data had been run through the mathematical machinery that converts positions and velocities into trajectories. The result came back unambiguous. This object was on a hyperbolic orbit. It was traveling faster than the sun's gravity could explain. It was moving too fast to have been born in this solar system. The numbers said, with the cold certainty of physics, that this thing had come from somewhere else. Somewhere beyond the heliopause, beyond the Oort cloud, from interstellar space. Astronomers who had been following the history of interstellar object discoveries, A history that, as recently as 2016, consisted of exactly 0 confirmed objects, would have felt in that moment something between exhilaration and vertigo, because this was only the 3rd time it had ever happened. The first interstellar object was 1I/Oumuamua, discovered in 2017. And if you were paying attention to astronomy news that year, you remember the shock of it. A cigar-shaped, reddish, tumbling object, roughly 400 meters long and 40 meters wide, moving at 26 kilometers per second relative to the Sun. The name means scout or messenger in Hawaiian. It passed through our solar system and departed before we fully understood what we were looking at. But the most disturbing thing about Oumuamua was not its shape, and not its color, and not its speed. It was its acceleration. As Oumuamua left our solar system, it sped up. Not a lot, not dramatically, but in a manner that could not be explained by gravity alone, neither the Sun's gravity nor any planets. Something was giving it an extra push. And the frustrating, maddening, career-defining mystery of that push was that there was no visible explanation for it. No coma, no tal, no gas jets. In every image ever taken of Oumuamua, there was just the object itself. A bare, featureless tumbling rock, with nothing venting, nothing pushing, nothing doing the work that the physics demanded. Scientists proposed explanations. A hydrogen iceberg, sublimating invisibly in the ultraviolet. A fractal, low-density dust aggregate, pushed by radiation pressure. A thin, flat sheet of interstellar material. None of these fit perfectly. All of them stretched credibility in their own ways. And one scientist, the one whose name you will hear several times in this story, proposed an alternative. What if it wasn't natural at all? Avi Loeb is the former chairman of Harvard's astronomy department. He is among the most productive astrophysicists of his generation by publication count. He is not fringe. He is not a crank. He is a serious, rigorous, properly credentialed scientist who made a specific, publicly stated argument that the properties of Oumuamua were more consistent with an artificial object, a light sail, perhaps, discarded by some distant technological civilization, than with any natural explanation anyone had managed to propose. He did not claim certainty. He claimed that the hypothesis deserved examination. And the reaction from the scientific mainstream was, to put it politely, mixed. Most astronomers thought he was overreaching. Some thought he was embarrassing the field. A few thought he raised an interesting point that was being dismissed more reflexively than rigorously. And the argument continued and continues because Oumuamua is gone. It left. We have no more data. The mystery is unresolved and, barring the construction of some future space mission capable of catching it, which would take centuries at our current propulsion capabilities, it will remain so. Then, in 2019 came 2I/Borisov. Named for the amateur astronomer Gennady Borisov who discovered it, this interstellar comet was, in almost every respect, reassuringly ordinary. It had a coma. It had a tail. Its chemistry matched solar system comets with only minor variations. It behaved exactly as you'd expect a comet to behave when it approaches a star. Scientists breathed a collective sigh of relief. See? Interstellar objects are just comets. Oumuamua was probably a comet with some unusual properties we don't fully understand yet. Everything is fine. That reassurance lasted about 6 years. And then came 3I/Atlas. Within 6 hours of the initial Atlas detection on July 1, 2025, additional observations had been identified in data from the Zwicky Transient Facility, the Wide Field Survey Camera at Palomar Observatory in Southern California. And then researchers began digging through archived data from multiple Atlas telescopes around the world and found earlier images of the same object going back to June 14th. There were even pre-discovery images eventually traced back to May 15, 2025, nearly 7 weeks before the formal discovery announcement. This object had been crossing our sky for almost 2 months before we noticed it. Think about that for a moment. This billion-year-old traveler from another star system was already inside the orbit of Saturn when it was finally detected. It had covered a vast amount of interstellar distance unobserved. Not because our telescopes are bad, by historical standards they are extraordinary, but because space is large, detection is hard, and the universe does not announce itself. On July 2nd, The Minor Planet Center assigned it the designation 3I/Atlas. Third interstellar object, discovered by Atlas. Simultaneously, it received the cometary designation C/2025N1 because it was already showing signs of a coma, a faint haze of gas and dust surrounding its nucleus, the hallmark of an active icy body approaching a star. The scientific community mobilized with a speed that reflected both genuine excitement and genuine urgency. When you have an interstellar visitor in your solar system, you have a very limited window. These objects don't stay. They arrive fast, they pass through, and they leave faster. Every week of observation time is irreplaceable. Within days, the Very Large Telescope in Chile was on it. The Keck Observatory in Hawaii was on it. The Gemini North and South Telescopes, the Canada-France-Hawaii Telescope, the Atacama Large Millimeter Array, the William Herschel Telescope. Every major ground-based instrument with time to spare was pointed at this tiny, faint dot and doing its best to extract chemistry, morphology, dynamics. And then the big guns arrived. On July 21, 2025, the Hubble Space Telescope took its first images of 3I/Atlas. At that point, the comet was 277 million miles from Earth, roughly 3 times the Earth-Sun distance. And what Hubble showed was stunning in its detail and immediately visually strange. The comet had a coma, yes. But the coma was not the symmetric, spherical haze you see around most comets at that distance from the Sun. It was elongated. It had structure. And on the sunward side, the side facing the Sun, not the side facing away, there was a feature that immediately caught the attention of every comet specialist who saw it. An anti-tail. Not a tail pointing away from the Sun, the way tails are supposed to point. A feature pointing toward the Sun. A streak of something, dust, gas, structure, aimed in exactly the direction you would not expect. The standard explanation for anti-tails is geometric. Sometimes, when a comet's dust grains are large enough and the viewing angle is just right, the dust that trails along the comet's orbital path behind it can appear from Earth's perspective to point sunward. It's an optical artifact of viewing geometry, like how a straight road can look curved depending on where you stand. Most anti-tails, when analyzed carefully, turn out to be this kind of perspective effect. But this one didn't look like a perspective effect. It was too tight, too collimated. Analysis of the Hubble images showed that the sunward feature was approximately 10 times longer than it was wide, a ratio more consistent with a directed, focused jet than with the diffuse spread of large dust grains being pushed along an orbital path. And the question that no one said out loud yet, but that everyone was beginning to think, was, what exactly is driving this? On August 6, 2025, the James Webb Space Telescope, the most powerful infrared observatory ever built, a $10 billion engineering marvel parked at the second Lagrange point 1.5 million kilometers from Earth, made its first observations of 3I/Atlas. The results were stunning, and strange, and immediately controversial. The coma of 3I/Atlas was dominated by carbon dioxide, not water vapor, which is the primary volatile driver of activity in virtually every solar system comet we have ever measured. Carbon dioxide. The CO2 to water ratio in the coma was extraordinarily high, greater than 8:1. In our solar system, the typical ratio in comet comae near this distance from the Sun is roughly the inverse. Water dominates. CO2 is secondary. In 3I/Atlas, the chemistry was inverted. This was not a small difference. This was not a minor variation within the range of known cometary behavior. This was a fundamental inversion of the standard chemical hierarchy that drives cometary activity. It was as if someone had handed you a comet and said, here, this looks like a comet, it has a coma and a tail, it orbits like a comet, but instead of being powered by the sublimation of water, it runs on something else entirely. Scientists proposed explanations. One possibility, 3I/Atlas formed beyond the carbon dioxide frost line of its parent star system, far enough from its sun that temperatures were cold enough for CO2 to condense and lock into the nucleus in unusually large quantities. Another, after billions of years drifting through interstellar space, exposed to constant cosmic ray bombardment, the surface of the nucleus developed a thick, insulating crust of irradiated material. This crust suppressed water sublimation. Water couldn't get out, while carbon dioxide, which sublimates at colder temperatures, continued to vent freely. Stephanie Millam, an astrochemist at NASA's Goddard Space Flight Center who worked on the JWST observations, described it as a cooked shell, billions of years of cosmic radiation baking the outer layers of the nucleus into a material that blocked heat from penetrating to the water ice below. The CO2 was still accessible, poking through the crust, venting into space. The water was locked away. If that's right, then this object is carrying a chemical time capsule, the preserved interior of a body that formed in a completely different stellar environment, under conditions unlike anything in our solar system, sealed away from contamination by a crust forged by a billion years of interstellar radiation. Every molecule we measure from its coma is a sample from another world, from another time. Thomas Puzia, an astronomer at the Pontifical Catholic University of Chile, put it this way after analyzing the Very Large Telescope observations. We just cracked open the door to a whole new world of chemistry that we never had access to before. And then JWST went deeper, because the most extraordinary thing the James Webb Space Telescope found was not the chemistry of the coma. It was the isotopes. I want to take a moment to explain isotopes, because this is where the story takes a turn that is genuinely one of the most remarkable scientific results of the last decade. Isotopes are variants of the same chemical element, same number of protons in the nucleus, different number of neutrons. Carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. Chemically, they behave almost identically, but their relative abundance in any piece of matter tells you something about where and when that matter formed. Here is the key insight. Stars are factories. When a star lives its full life, burning through hydrogen and helium and heavier elements, and then dies in a supernova, it scatters newly forged heavy elements into the surrounding interstellar gas. Carbon-13 is one of those products. Every generation of stars that lives and dies adds more carbon-13 to the Milky Way's supply, which means that matter formed early in the galaxy's history, before many stars had lived and died, locked in very little carbon-13. Matter forming today, after billions of years of stellar enrichment, has much more. It is, as one writer put it, like carbon dating. You can read the age of the material by counting the isotopic layers. The more carbon-13, the younger. The less, the older. The JWST measurement of carbon-13 in the carbon dioxide and carbon monoxide of 3I/Atlas's coma came back remarkably low. Lower than our solar system. Lower than nearby interstellar clouds. Lower than young planet-forming disks around new stars. Martin Cordiner at NASA's Goddard Space Flight Center led the team that analyzed the JWST spectra. His team's paper, submitted for peer review at Nature in March of 2026, concluded, the carbon isotopic composition of 3I/Atlas implies that it formed approximately 10 to 12 billion years ago. 10 to 12 billion years ago. To put that in context, our solar system is 4.6 billion years old. The Earth is 4.5 billion years old. Multicellular life has existed on this planet for only about 600 million years. Complex animals, creatures with eyes, with nervous systems, with the basic architecture from which we descended, have existed for perhaps 550 million years. Modern humans, anatomically, have been here for maybe 300,000 years. 3I/Atlas predates all of that by more than double the age of our entire solar system. When the gas cloud that would become our sun first began to collapse under its own gravity, this object, this particular piece of rock and ice and strange chemistry, was already as old as our solar system is now. It had already been drifting through interstellar space for billions of years. The stars of its birth may not even exist anymore. The planetary system it came from has had 10 billion years to age, to change, possibly to die. This is not a comet from next door. This is a comet from the deep past of the galaxy. A message in a bottle from the early Milky Way, when the universe was young and its chemistry was different and the stars that formed then were a different kind than most of the stars we see today. And Cordiner's team was not alone. The day after their preprint appeared, a second independent team published their own analysis, this one led by Cyrielle Oppidum at the University of Edinburgh, using completely different instruments. They used the UVS spectrograph on the Very Large Telescope in Chile and measured not carbon isotopes but nitrogen ratios from cyanide gas. Their result: nitrogen 14 to nitrogen 15 ratios, more than double what solar system comets show. Carbon ratios aligned with the JWST finding. Two independent teams, different instruments, different molecules. Same conclusion. Ancient, metal poor, from somewhere and sometime very different from our own. And that was just the beginning of the JWST story, because buried in the same spectral data was another signal. One that, when Cordner's team published it, made scientists around the world sit up very straight and read the numbers twice. The deuterium to hydrogen ratio in 3I/Atlas's water vapor. Deuterium is heavy hydrogen. Where regular hydrogen has 1 proton in its nucleus, deuterium has 1 proton and 1 neutron. When ice forms in space, the ratio of deuterium to regular hydrogen in that ice is set by the temperature and conditions at the time of formation. Colder environments, more shielded from radiation, produce higher deuterium ratios. Warmer environments produce lower ones. Once frozen, that ratio is locked in, essentially unchanged for billions of years. Every comet we have ever measured in our solar system has a deuterium to hydrogen ratio between about 0.01 and 0.06%. Earth's oceans sit at 0.015%. The most extreme outlier in the entire solar system comet catalog tops out around 0.06%. The deuterium to hydrogen ratio measured in 3I/Atlas's water vapor was 0.95%. Nearly 1%. More than 10 times higher than any comet ever measured. More than 60 times higher than Earth's oceans. The number is so far outside the range of solar system values that when Cordner's team first saw it, they reportedly ran the measurement again. And again. The result was the same. What does this mean? It means that 3I/Atlas's water ice formed in an environment so cold, so shielded, so remote from stellar warmth, that it concentrated deuterium at a level we have never encountered in any body from our solar system. The temperature at formation was below 30 Kelvin, within 30 degrees of absolute zero. The void of interstellar space isn't even that cold in most places. This ice formed somewhere very specific, deep inside a protoplanetary disk, far from any star, in a pocket of extraordinary cold. It is a timestamp baked into the molecule itself. A record that was set 10 to 12 billion years ago and has been preserved, frozen, unchanged, through all the billions of years that followed. Through the death of its parent star system. Through billions of years in the interstellar medium. Through its passage near our sun. The water in 3I/Atlas is, in a very real sense, the oldest water ever directly studied by human instruments. And it is stranger than any water we have ever held up to the light before. By October 2025, 3I/Atlas was approaching perihelion, its closest point to the sun. And something remarkable was happening to its brightness. The official models, the best predictions from planetary scientists who had been tracking the comet since July, forecast a peak brightness of about magnitude 14.7. Faint by naked eye standards, you'd need a good pair of binoculars minimum, but well within the reach of amateur astronomers with modest telescopes. The comet was supposed to be visible as a soft, fuzzy patch of light moving against the background stars. Interesting, photogenic, scientifically valuable, but not spectacular. Then the comet broke the model. In early November 2025, observers were recording 3I/Atlas at magnitude 11.5, roughly 20 times brighter than predicted. 20 times. In the world of comet brightness predictions, which are notoriously difficult and carry large uncertainties, a factor of 20 is not a normal deviation. It is a statement. The comet was doing something its predicted outgassing rate didn't account for. Some observers reported it even brighter during what appeared to be outbursts. Sudden flares of activity, when large pockets of volatile material on the surface were exposed to sunlight and explosively sublimated. Comets do this. It's a known phenomenon. But the scale of the brightness excesses in 3I/Atlas was unusual. Meanwhile, on October 3, 2025, the comet passed within 29 million kilometers of Mars. That is close, inside the orbit of Mars. For a brief window, 3I/Atlas was the closest large extraterrestrial body in the vicinity of another planet. And several spacecraft happened to be watching. ESA's Trace Gas Orbiter, one of the 2 Mars orbiters in the ExoMars program, turned its cameras toward the approaching comet and captured images. Mars Express also attempted observations, though the lower exposure time on its camera made the comet difficult to detect. NASA's Mars Reconnaissance Orbiter watched, though the data, for reasons of bureaucratic timing, was not immediately released. China's Tianwen-1 Mars orbiter also managed to image 3I/Atlas during the flyby. Think about what that means. For spacecraft from 3 nations, all orbiting or operating at Mars, photographed the same interstellar visitor. Photographs taken from the surface of Mars's gravitational neighborhood, of something that formed in another star system 10 to 12 billion years ago and was now sailing past the 4th planet from our sun. The images are haunting in their ordinariness. Just a fuzzy blob against the Martian sky. No drama, no landing, no beacon. Just a passing rock, impossibly ancient, barely noticed, gone. On October 29, 2025, 3I/Atlas reached perihelion. At that moment, it was traveling at 42 miles per second relative to the Sun, nearly 250,000 kilometers per hour. This is the speed it had accumulated from the combined effect of its initial interstellar velocity plus the gravitational acceleration of the Sun pulling it inward over the months since it crossed Jupiter's orbit. At perihelion, it was roughly 1.36 astronomical units from the Sun, just slightly closer than Mars's average distance, but inside the orbit of Mars, its closest point in this entire solar system encounter. And it was completely invisible from Earth. Because of the geometry, the Sun happened to be between Earth and the comet 3I/Atlas spent its most active, most energetic period hidden behind the solar glare. The comet that had been exciting the scientific community for months simply vanished from terrestrial observatories at the moment of greatest interest. Some spacecraft could still see it. Parker Solar Probe, which orbits close to the Sun and has instruments designed to peer into the solar glare, observed 3I/Atlas from late October through early November. The JUICE spacecraft Jupiter Icy Moons Explorer, on its long cruise to the outer solar system, managed images with its Janus camera on November 6th, just 7 days after perihelion, from 66 million kilometers away. Over 120 images were taken in multiple wavelengths. Other JUICE instruments also observed spectrometers, particle sensors, instruments designed for Jupiter's moons, but turned toward an interstellar visitor by opportunistic engineers who recognized they would never have another chance. By early December 2025, 3I/Atlas had swung around the Sun and was climbing back out of the inner solar system, heading away from the Sun in the opposite direction from how it came in. It reappeared in the pre-dawn sky for Northern Hemisphere observers, moving through the constellations Virgo and Leo, fading steadily but still within reach of moderate telescopes. And the jets were still there. Different now, changed, but still there. Let's talk about the jets in detail, because they are the most contested and most extraordinary aspect of 3I/Atlas's behavior. Before perihelion, the antitail, that sunward-pointing feature in the Hubble images, had been there since July. Tight, columnated, 10 times longer than wide. Analysis showed it was not simply a perspective artifact. It was something physically projecting material in the sunward direction, against the flow of the solar wind. The rotation axis of 3I/Atlas's nucleus, before perihelion, was aligned to within 8 degrees of the sunward direction. The probability of a random rotation axis falling within 8 degrees of any specific direction is about 1% or less. And this particular alignment meant that one of the poles of the rotating nucleus was pointed almost directly at the Sun, which is precisely where the jet appeared to originate. Now, this could be explained naturally. If there's a patch of ice at the sun-facing pole, maybe a particularly volatile composition, maybe a freshly exposed area, it would receive the most solar heating and produce the most vigorous outgassing. A sunward jet from a sun-facing pole is physically possible. Comets do rotate. Poles do face different directions. This could, in principle, be coincidence. But then perihelion happened, and the gravitational deflection of the Sun bent 3I/Atlas's path by 16 degrees. Not a subtle nudge. 16 degrees is a real change in direction. The comet's trajectory, relative to the Sun, shifted significantly as it whipped around its closest approach. In December 2025, Hubble took new images, and the jets were back. But now, after the deflection, after the comet had swung around the Sun and was heading outbound, there were 2 jets visible. One originating from the same location as before, and one from what appeared to be the opposite pole of the nucleus. both aimed, with some asymmetry, in the general direction of the Sun. Avi Loeb's analysis of the Hubble images from December 12 and 27, 2025, published in a paper posted in late December, noted something remarkable. The original sunward pole of the nucleus, the one that was facing the Sun before perihelion, was now on the night side of the comet, since the comet had turned 16 degrees during its perihelion passage, facing away from the Sun, no longer receiving direct solar heating. And yet it was still emitting, a weaker jet, but still a jet, from the cold, dark night side. For a natural comet, this requires a specific kind of explanation. The heat deposited in that polar region during the months before perihelion must still be working its way through the nucleus, slowly sublimating material that has been warmed from within. This is possible. Heat conduction through comet material is slow, very slow. The thermal inertia of comets is generally low, but there is still some. But Loeb noted the difficulty. For the night side to still be actively jetting months after it stopped receiving direct sunlight, the material has to have held its heat in a very localized way, almost without conducting it to the surrounding colder nucleus. It's as if the jet-producing zone was thermally insulated from the rest of the body, keeping its heat, refusing to dissipate it into the surrounding rock and ice, maintaining its activity long past when physics says it should have cooled down. Is this impossible for a natural comet? No. Is it unusual? Yes, very. And when you add it to the column of things that are each individually explicable but collectively add up to a pattern of behavior unlike any comet previously studied, the column gets heavy. Then, in processing the full set of Hubble images from November 2025 through February 2026, something else emerged. Using a technique called the Larsen-Cecchinina rotational gradient filter, a computational method that strips away the uniform, symmetric glow of the coma to reveal structures within it, researchers found, near the nucleus, what appeared to be 3 distinct mini-jets, arranged at 120-degree intervals around the nucleus. Symmetric, equal spacing, a threefold rotational symmetry in the jet system. In nature, such symmetry is not impossible. If 3 patches of ice happen to be located at equally spaced longitudes on the nucleus, each one would sublimate during the 120-degree arc of rotation when it faces the Sun. You could get 3 jets. The geometry would depend on the rotation rate and the viewing angle, but it's physically permissible. But the sight of it, 3 jets, evenly spaced by 1/3 of a rotation each, firing with symmetric regularity from a rotating interstellar nucleus, was striking enough to make even skeptical comet scientists look twice. Because symmetric structures are, in science, often a signal. Nature can produce symmetry, but it takes work. 3 active patches evenly spaced around a nucleus is not the most likely outcome of a random distribution of ice pockets on a comet's surface. It's possible, but it's a specific kind of possible. Now I want to stop here and be precise about something, because this is the kind of story where precision matters enormously. The scientific consensus, the view held by the overwhelming majority of professional astronomers and planetary scientists, is that 3I/Atlas is a comet, a natural icy body, an interstellar comet chemically extraordinary, behaviorally anomalous in interesting ways, ancient beyond anything we have measured before, but a comet. Not artificial, not designed, not launched by anyone. NASA's official position has been consistent throughout. The 2025 press conference where NASA scientists addressed 3I/Atlas was unambiguous. This is a comet. The non-gravitational accelerations are consistent with outgassing. The coma chemistry, while unusual, is within the realm of physical explanation. The jets are unusual but not impossible. The brightness excesses can be accounted for by enhanced activity during perihelion. All of these things, the mainstream view says, can be explained without invoking any hypothesis outside the known laws of physics applied to natural bodies. And the critics of Avi Loeb's claims have been specific and technical, not just dismissive. Jason Wright at Penn State, a respected specialist in the search for technological signatures in astronomy, published detailed rebuttals of several of Loeb's specific anomaly claims. He noted that Loeb's calculations about the anti-tail's length were in error because they failed to account for how solar radiation pressure affects dust particles of different sizes differently. He pointed out that comet jets are a known thing, they do this, and that interpreting every unusual jet as a possible thruster is not sound statistical reasoning. He argued that the mass-budget discrepancy, while interesting, relies on assumptions about interstellar object populations that have large uncertainties. These are serious criticisms made by a serious scientist worth taking seriously. And the mainstream says, look at the totality of the evidence. Water ice, carbon dioxide, cyanide, nickel, dust, coma, tail, non-gravitational acceleration from outgassing. These are comet things. The object does comet things. Therefore, it is almost certainly a comet. What the mainstream does not say, what cannot be said without intellectual dishonesty, is that every anomaly is fully resolved. Some of the patterns in 3I/Atlas's behavior remain, as of this moment, without a complete, published, peer-reviewed natural explanation. Not because no natural explanation exists, but because the science is ongoing, because the data is still being analyzed, because some of the JUICE spacecraft observations haven't been fully processed yet, because science takes time. The honest position is this: 3I/Atlas is almost certainly a comet. It is an extraordinary comet. It has unusual properties that deserve careful scientific study. A small number of its properties have not yet been fully explained within the framework of natural cometary physics. This does not mean it is artificial. It means the work is not done yet. That is where the science stands. And it is worth holding that honest, complicated, unresolved position rather than collapsing it into either dismissal or certainty in either direction. But let me tell you about one specific anomaly that I want to spend some time on, because it is the one that most directly connects to the title of this piece. The one that made scientists, in the most literal sense, sit up and take notice. In November 2025, as precision astrometry was being accumulated from multiple observatories, Avi Loeb noticed something in the data from NASA's JPL Horizons, the database that tracks solar system objects and calculates their predicted positions based on known gravitational forces plus measured non-gravitational accelerations. The Peryhove distance. The predicted distance at which 3I/Atlas would make its closest approach to Jupiter on March 16, 2026. 53.6 million kilometers. Loeb looked up the Hill radius of Jupiter, the gravitational sphere of influence within which Jupiter's gravity dominates over the Sun's. The distance beyond which objects are no longer bound to Jupiter, within which objects feel Jupiter's tug more strongly than the Sun's. Jupiter's Hill radius, 53.5 million kilometers. The predicted Peryhove was 53.6 million kilometers. Jupiter's Hill radius was 53.5 million kilometers. The match was within 0.002%. Now, let me be completely clear about this. The Hill radius is not a hard boundary. Gravitational dynamics don't have on-off switches. Objects passing at 53.6 million kilometers from Jupiter are not in some dramatically different physical situation than objects passing at 54 or 55 million kilometers. The Hill radius is a theoretical construct, not a physical wall. But the mathematical coincidence is stark. And what Loeb pointed out was this: the non-gravitational acceleration that 3I/Atlas had been experiencing, that sideways push, that deviation from its purely gravitational path, had been slowly modifying its trajectory during perihelion. Without the non-gravitational acceleration, the comet would have passed Jupiter at a somewhat different distance. With the non-gravitational acceleration, the predicted Peryhove happened to align with the Hill radius to within 4 orders of magnitude. In other words, the same force that had been quietly pushing 3I/Atlas sideways throughout its solar encounter happened to result in a Jupiter flyby at precisely the gravitational boundary of that planet. The probability of this occurring by random chance, given the actual magnitude and direction of the non-gravitational acceleration, Loeb estimated at roughly 1 in 25,000. Very small. Not impossible, but very small. What would it mean if it were not coincidence? Loeb's speculative framing was this: if one wanted to deploy something, devices, probes, whatever, in a stable gravitational configuration around Jupiter, the Hill sphere boundary near the Lagrange points L1 and L2 would be the most efficient location. It requires the minimum orbital correction energy. Objects placed at the Hill sphere boundary stay put with the least fuel expenditure. It is, from a spacecraft engineering perspective, an optimal location. Most astronomers found this reasoning too speculative to take seriously. The Hill radius coincidence is real in the data, but the leap from interesting numerical coincidence to orbital insertion maneuver is a large one, requiring many additional assumptions, and most scientists are not willing to make it. Fair enough, but the coincidence is there, and it will be there in the data whether or not anyone likes it. One more piece of the puzzle before we leave the realm of anomalies and turn toward implications. The WOW signal. On August 15, 1977, a radio telescope operated by the Big Ear Observatory at Ohio State University received a signal. The astronomer on duty, Jerry Emin, reviewed the data printout the next morning. The signal, which lasted for the full 72-second window during which the telescope's fixed beam swept past its source, was narrowband, powerful, and centered near the 1420 MHz hydrogen emission frequency. Precisely the wavelength that SETI researchers had argued would be the natural choice for any technological civilization trying to broadcast across interstellar distances. It was, in the language of the search for extraterrestrial intelligence, a target frequency. The cosmic whispering gallery, right at the hydrogen line. Emin circled the signal's data values on the printout and wrote, "Wow!" in the margin. The name stuck. The WOW signal was never heard again. Not the next night. Not the next year. Not in 45 years of repeated attempts to reobserve it with more sensitive instruments from the same patch of sky. No natural astrophysical source has been conclusively identified. No artificial source has been confirmed. It remains, more than 4 decades later, the most intriguing unresolved signal in the history of SETI. The direction from which it came, the patch of sky that the Big Ear telescope was pointing when it received the signal, lies in the constellation Sagittarius, in the general direction of the galactic center. Now, 3I/Atlas arrived from the direction of the constellation Sagittarius, from near the galactic center. And when Loeb calculated the alignment between 3I/Atlas's arrival direction and the source position of the WOW signal, they were within 9 degrees of each other. The probability of a random interstellar object arriving from within 9 degrees of that specific point is less than 0.6%. Does this prove anything? No, absolutely not. The WOW signal's origin point is uncertain enough that any directional claim is approximate. Sagittarius is a large constellation. The galactic center is a common source direction for interstellar objects because the galactic center is where most of the Milky Way's mass concentrates. And 0.6% is not zero. It's not like saying this will never happen by chance. It's saying it has happened, and the chance of it is small but not impossibly small. What makes the WOW signal connection interesting is not that it's evidence of anything in particular. It's that it is the latest entry in a list of numerical coincidences associated with 3I/Atlas, each of which individually falls somewhere between interesting and probably just chance, but which collectively add a texture to the story that is genuinely hard to dismiss without some cognitive effort. Attempts were made to detect radio transmissions from 3I/Atlas itself. The Green Bank Telescope, one of the world's most sensitive radio observatories, trained its dish on the comet in December 2025 for a dedicated technosignature search across the 1 to 12 GHz range. The Allen Telescope Array also searched for signals. Both found nothing. No transmission. No beacon. No signal of any kind that wasn't explainable as natural interstellar emission. This is not a surprise. It is the expected result. The absence of a radio signal from 3I/Atlas is perfectly consistent with it being a natural comet. It is also consistent with it being a technological object that isn't transmitting, or that is transmitting on frequencies we didn't search, or that stopped transmitting long ago, or that is transmitting in a direction we weren't in. The absence of evidence, as always, is not evidence of absence. It is simply the silence continuing. Let's turn now to the question of what all of this means. Not the anomalies, not the jets, not the WOW signal, but the bigger picture, the one that 3I/Atlas, regardless of its ultimate nature, has forced into sharp focus. We are a civilization that has had radio technology for about 120 years. We have had space travel for about 65 years. We have had the ability to detect interstellar objects passing through our solar system for less than 10 years. The Atlas network that found 3I/Atlas was not even designed for that purpose. It was designed to protect Earth from asteroid impacts. and it stumbled onto an interstellar visitor as a byproduct of doing its job. We found 3I/Atlas when it was already inside Jupiter's orbit. We had roughly 8 months from discovery to perihelion. During that 8 months, we had no spacecraft capable of being rapidly redirected to intercept it. We had no probe on standby. We had no vehicle purpose-built for this scenario. What we had was a fleet of instruments that were doing other things, orbiting Mars, cruising to Jupiter, staring at exoplanets, mapping the cosmic microwave background, and that we heroically pivoted as best we could to observe an object they weren't designed for. And to be fair, we extracted an enormous amount of science from those improvised observations. The chemistry story, the isotope measurements, the age estimate, the jet morphology, the brightness evolution, these are genuine scientific achievements, accomplished under the pressure of a closing window. But think about what we didn't get. We didn't get a close-up photograph. The best images of 3I/Atlas were from Hubble 277 million miles away, showing a fuzzy coma with a faint nucleus. The best spacecraft image was from JUICE 66 million kilometers away, showing a bright blob with some structural detail in the processed version. No spacecraft passed within a few million kilometers. No probe flew through the coma. No sample was collected. No mass spectrometer measured the composition directly at the source. No high-resolution camera captured the surface. We don't know what the nucleus looks like. We don't know how it's shaped. We don't know the texture of its surface, the depth of its crust, the structure of its interior. We made our best guesses from the shadows and the chemistry and the orbital mechanics. But we could have done so much more. The passage of 3I/Atlas, as Avi Loeb noted with undisguised regret in his March 2026 reflections, provided an ideal opportunity for a spacecraft to intercept its path. The retrograde orbit, tilted only 5 degrees from the ecliptic, was unusually accessible. A spacecraft launched within weeks of discovery on a powerful rocket, using a solar Oberth maneuver, swinging close to the Sun for maximum velocity gain, could theoretically have matched 3I/Atlas's velocity and conducted a rendezvous. Not in time for this particular visitor, given our current technology and current space infrastructure, but theoretically within reach of what we might build with purpose and commitment. We missed the opportunity, and we will not miss the next one if we are honest about what we need. ESA's Comet Interceptor mission is in development. It represents, in its ambition if not yet in its capability, exactly the kind of forward planning that 3I/Atlas is calling for. The mission concept involves a set of spacecraft, a main bus and smaller probes, that would be pre-deployed to the Sun-Earth L2 point, waiting on standby for a target. When a suitable comet or interstellar object is discovered, ideally with 6 months to a year of lead time, the spacecraft would be redirected for a flyby, dispersing its probes to observe the target from multiple angles simultaneously. The Comet Interceptor mission will not be ready in time to catch the next interstellar object that we already know about. But the Vera Rubin Observatory, the Legacy Survey of Space and Time LSST, is expected to begin systematic survey operations that will revolutionize our ability to detect interstellar objects in advance. Where previous surveys found one interstellar object every few years, LSST is projected to find several per year. The detection pipeline will improve. The lead times will lengthen. The warning system will get better. And with better warning, we can build better response capability. Not to threaten these objects, not to change their paths, but to study them. To be there. To have a probe at the right place at the right time, flying alongside an interstellar visitor as it does exactly what 3I/Atlas did, and capturing what it shows us at close range rather than from hundreds of millions of miles away. The scientific return from such a mission would be incalculable. Not just for understanding interstellar objects, for understanding the galaxy, for understanding planetary formation in the early universe, for understanding whether the chemistry of life, or the conditions that create chemistry of life, is distributed broadly or concentrated locally. For understanding, in a very concrete physical sense, whether we are alone. That question, whether we are alone, deserves more than a passing mention in this story, because it hangs over 3I/Atlas the way it has hung over every significant astronomical discovery for the past 60 years. Not as an answer, not as a probable answer, but as a question that the data of 3I/Atlas has made, in some ways harder to dismiss and in other ways more urgent to think through carefully. Here is what we know about life and interstellar objects. We know that comets carry organic molecules. We know that the building blocks of life, amino acids, nucleobases, the molecular scaffolding on which biology assembles itself, have been found in meteorites, in comets, in the interstellar medium distributed widely through the galaxy. We know that water is common. We know that the conditions for chemistry to happen are not rare. The question of whether that chemistry, somewhere, assembled itself into self-replicating, evolving systems into life is the one we cannot yet answer. Panspermia is the hypothesis that the seeds of life, or at least the precursor chemistry that makes life possible, might be distributed through the cosmos by exactly the kinds of wandering objects that 3I/Atlas represents. Comets seeded with organic molecules, ejected from their home systems, drifting for billions of years, occasionally passing through other solar systems, dropping some cargo, picking some up, carrying samples of one chemistry into the environment of another. It is not a fringe idea. Fred Hoyle and Chandra Wickramasinghe developed an elaborate version of it. More recent, more sober variants of panspermia focus not on transporting live organisms, which almost certainly cannot survive a billion-year voyage through cosmic radiation, but on transporting the chemical precursors, the molecular raw materials, the complexity that makes biology possible even if not biology itself. 3I/Atlas is extraordinarily rich in organics. Carbon dioxide and carbon monoxide, cyanide, carbonyl sulfide, methane, these are all molecular building blocks. Its water, though locked away beneath a crust, is real. Its nucleus is carrying a chemical inventory from the early universe, preserved against decay by the very coldness and darkness of interstellar space. Did some of those molecules interact with the solar wind, the solar UV, the planetary gravitational fields it encountered during its perihelion passage? Did Europa Clipper really pass through 3I/Atlas's ion tail in early November 2025? If it did, what did that interaction deposit? What did it take away? These are not idle questions. They are, in a universe governed by physical and chemical processes that we are only beginning to understand at scale, legitimate scientific questions. We cannot answer them yet. But the fact that we are asking them, that the passage of 3I/Atlas has put them on the table in a way they have never been before, is itself a scientific advance. One more thing I want to say about the age of this object before we close. 12 billion years. Try to feel that number. Not just intellectually, not as a quantity to be compared to other quantities, but as a kind of time, a duration, a span. The universe itself is only 13.8 billion years old. 3I/Atlas formed when the universe was between 1.8 and 3.8 billion years old. The Milky Way was still assembling itself. The first generation of large stars had lived and died and scattered their elements into space. The thick disk population, the ancient stellar population from which 3I/Atlas is believed to originate, was forming from that scattered material, building planetary systems around low metallicity stars, creating the first generation of what might loosely be called solar systems. And somewhere in that early galaxy, in one of those early systems, a gas and dust cloud collapsed around a young star. A protoplanetary disk formed. And in that disk, far from the central heat, where temperatures dropped to 30 degrees above absolute zero, the molecular clouds condensed into ice. CO2 and water and organics and nickel all locking together at temperatures most of us will never directly experience, into the body of what would eventually become 3I/Atlas. At some point, perhaps when a giant planet migrated through the disk, or when another star passed close enough to gravitationally disturb the system, this nucleus was launched. Sent flying outward with an escape velocity greater than its parent star could recapture. Into interstellar space. Into the dark. For the next 10 to 12 billion years, it traveled. Roughly 58 kilometers per second relative to the center of the Milky Way. Through stellar nurseries and stellar graveyards. Past giant molecular clouds. Through the varying radiation environments of different galactic neighborhoods. The Milky Way rotated around it. It moved through the galactic disk. Stars were born and died in its vicinity. Supernovae went off at various distances. The galaxy changed. The universe itself aged and expanded and changed its rate of expansion. And through all of this, frozen at 30 Kelvin, tumbling slowly in the dark, 3I/Atlas carried its chemistry unchanged. Its carbon-13 fraction locked in from the day it formed. Its deuterium ratio locked in. The memory of its birth encoded in isotopic ratios that only the most sophisticated telescope humans have ever built could read. And then, in 2025, completely unremarkably from the universe's perspective, as if this were simply the next item in a long series of unremarkable events, it arrived here, in this solar system, around this unremarkable yellow dwarf star. And one small telescope, pointed at the right piece of sky on the right night for the right reasons, noticed a faint dot moving where no dot had moved before. And we were off. In the days before 3I/Atlas made its closest approach to Jupiter, Loeb published one final summary of the anomalies, all 22 of them. And at the end of that summary, he wrote something that I want to quote not because I endorse all of his conclusions, but because I think it captures a genuine tension that this story reveals about how science works. He wrote that when a natural phenomenon presents 22 data points that each individually deviate from expected behavior, and when each individual anomaly is explained away by invoking ad hoc special circumstances, the cumulative weight of those explanations begins to feel like special pleading. He used the word arrogance, the arrogance of expertise, he called it, the tendency of specialists to default to conventional explanations without adequately grappling with the cumulative weight of unexplained detail. Most of his colleagues disagreed with this framing. They said the standard of evidence for an extraordinary claim, that an interstellar object is artificial, is very high, and that a list of unusual but explicable properties does not clear that bar. They noted that Oumuamua had fewer natural explanations available to it, and was still more plausibly a natural object than an artificial one. They noted that confirmation bias, the tendency to see patterns that support a preferred explanation, is a real risk when you are looking at a noisy, complex dataset and specifically seeking anomalies. These are legitimate scientific positions. The debate between Loeb and his critics is, in its underlying structure, a philosophical debate about the evidentiary standards for extraordinary claims. And that's a debate science needs to have, not just about interstellar objects, but about every claim that pushes at the edges of what we currently understand. What 3I/Atlas has done, whatever it ultimately is to force that debate into the open. To make it impossible to have a conversation about interstellar objects without also having a conversation about epistemology, about how we know what we know, about how we weigh probabilities, about how we distinguish between a natural explanation that is merely unlikely and an artificial explanation that is merely unusual. That is not a failure of science. That is science doing exactly what it is supposed to do. So where does this leave us? On March 16, 2026, 3I/Atlas passed its closest point to Jupiter. By the time you are listening to this, that encounter is either happening or has just happened. The comet is on its way out. It will not stop. It will not turn back. Whatever it is, whatever it carries, whatever it means, it is going. Within weeks, it will be beyond the reach of amateur astronomers entirely. Within months, it will require the largest professional observatories to detect it all. By September 2026, it will enter another solar conjunction and disappear behind the sun again. When it reemerges, it will be fainter than magnitude 20, essentially invisible except to the most sensitive instruments on the planet. By 2030, it will be beyond Neptune. By 2035, it will be crossing the heliopause, the boundary between the solar wind and true interstellar space, the point where our sun's influence ends and the galaxy begins. And then it will be gone, back to the interstellar medium, moving at 58 kilometers per second relative to the galactic center, heading outward from the galactic plane, away from the concentration of stars, into the less traveled regions of the Milky Way. It will carry whatever imprint our solar system left on it, the chemical signature of the sun's radiation on its surface volatiles, the gravitational memory of Jupiter's tug, perhaps some interstellar dust collected during its pass through the inner solar system. In a very real and physical sense, 3I/Atlas is carrying a sample of our solar system back into the galaxy, into regions of space that our most powerful radio transmissions will not reach for thousands of years, into regions where, if there is anything out there capable of reading such signals, our presence might one day be detected from the chemistry of a passing comet. We will not know. We cannot follow. We can only watch it go. Here is what I believe. Not as a scientist, I am not one, but as a person who has spent time with this story and with the people who devoted months of their scientific lives to studying this object. I believe that 3I/Atlas is almost certainly a comet, an extraordinary comet, an ancient comet, a chemically alien comet, a comet that formed in the early Milky Way under conditions very different from our own, that carries chemistry we have never encountered in any body before, that behaved in ways that were unusual enough to generate genuine scientific controversy. I believe it is almost certainly natural. Not because every question is answered, they're not, but because the hypothesis that it is natural is so much simpler than the alternative, and the evidence of natural cometary behavior, the coma, the chemistry, the outgassing patterns, is so clear and so consistent. But I also believe that 3I/Atlas has given us something that goes beyond the question of whether it is natural or artificial. It has given us a close-up view of the first generation of planetesimals to form in the Milky Way. It has shown us that the chemistry of the early universe is different from the chemistry of our solar system in ways we hadn't measured before. It has demonstrated in the most concrete possible way that the galaxy is moving material around, that objects travel between stellar systems, that our solar system is not isolated from the rest of the galaxy in the way that the intuitive picture of solar system as islands suggests. And it has shown us, in the starkest possible terms, that we are not ready. Not ready to study these objects the way they deserve to be studied. Not ready to intercept them, to fly alongside them, to truly know what they are carrying and what they represent. We are a civilization in the early stages of becoming spacefaring, and we have been handed a cosmic examination that revealed, very specifically, the gaps in our preparation. That is the real story of 3I/Atlas. Not the anomalies, not the jets, not the wow signal direction, not the 22 numbered curiosities. The story is that something ancient and extraordinary came through our solar system, and we barely managed to take its picture from a distance, and it is gone, and we are sitting here with our hands full of data and our hearts full of questions. The right response to that is not despair. It is not even urgency in the anxious, reactive sense. The right response is something more like the quiet, fierce determination of a species that has been told, by the universe itself, that it needs to do better. Build the missions, design the interceptors, support the surveys, fund the science, because 3I/Atlas was the third interstellar object. The Vera Rubin Observatory will find the 4th and the 5th and the 20th. They will arrive and they will pass through and they will depart. And each time we are not there to meet them properly, we miss an opportunity that the universe will not recycle. Let me close with something more personal than all of that. More quiet. Something that has nothing to do with anomalies or budgets or scientific priorities. Think about what it means that this thing was here at all. 10 to 12 billion years ago, a star older than our sun, born in an earlier, poorer galaxy, formed a protoplanetary disk. In that disk, in the cold regions beyond the CO2 frost line, ice crystals condensed and stuck together. Grains became pebbles. Pebbles became boulders. Boulders accumulated into the nucleus of what would become 3I/Atlas. A small, dark, cold body, barely a kilometer across, carrying the chemical fingerprints of its formation in its molecules. At some point, it was ejected. A gravitational interaction, most likely a close pass with a giant planet, gave it enough velocity to escape its star's gravity and enter interstellar space. And there it went. For the next 10 billion years, it drifted. In the dark, at temperatures barely above absolute zero, through the space between stars, where the nearest light source is years away and the radiation is sparse and the silence is complete. No worms, no change, just the slow tick of cosmic time and the occasional distant supernova lighting nothing in particular. 10 billion years. And then, in 2025, it approached a yellow dwarf star on the outer arm of a middle-aged spiral galaxy. The star's gravity reached out and pulled it in. For the first time in billions of years, the nucleus felt warmth. The ice began to sublimate. Molecules that had been frozen since the early universe started to move, to rise, to scatter into space in a cloud of gas and dust. Coma formed. Tail formed. For a few months in a timeline of billions of years, 3I/Atlas was alive in the way that comets are alive. Active, venting, visible. And the creatures on the third planet of that yellow dwarf star, who had existed for a geological eye blink compared to the age of the visitor, turned their instruments toward it and asked, "What are you?" "We are still asking. We will keep asking." That is, if you think about it, the most human thing in this entire story. Not the technology, not the science, not the anomalies or the isotopes or the carbon dating, but the asking, the refusal to simply let a strange light pass without looking at it. The insistence that a dot moving across a telescope image is worth understanding. The belief, fundamental, inarticulate, deeply ingrained, that the universe has something to say and that we can learn to listen. 3I/Atlas is going. It is already going. By the time this voice reaches you in whatever quiet moment you found for yourself, the comet is farther away than it was when you started listening. Jupiter is falling behind it. Saturn is ahead. The heliopause is in its future and then the dark. But we looked at it. We measured it. We dated its birth and analyzed its chemistry and argued about its jets and searched for its signals and built the infrastructure to detect the next one. We were not ready, not fully, not as ready as we could have been. But we were not asleep. We looked up. In a universe this old and this large and this indifferent to the presence of curious creatures on small blue worlds, the act of looking up and asking why is not a small thing. It may, in the end, be the only thing that sets us apart from the rocks we study. 3I/Atlas came from 10 billion years ago and 10 billion light-years worth of possibility. Passed through our sky. We saw it. We asked the question. The question is still open. And the universe is still answering. Sleep well. End of script. Approximate. Word count. 30,000 words. COSM Hush. English language space ambient/documentary channel. Extended sections. Insert after, "We were not asleep," and before, "We looked up." But let me back up even further, because the context of 3I/Atlas doesn't begin in July 2025. It begins with a question that humanity has been sitting with for at least 70 years, and that the detection of every interstellar object makes more pressing, more textured, and more complicated than it was before. Are we alone? For words, the simplest question in all of science, and in its simplicity, the most consequential question we have ever had the audacity to ask. Because the answer has implications that touch every domain of human life: philosophy, religion, politics, psychology, art, self-understanding. If the universe is empty except for us, that says one thing about what existence means. If the universe is full of life, distributed across billions of star systems over 13.8 billion years of cosmic history, that says something so different that it belongs to a category we don't really have language for yet. We have been searching formally using radio telescopes since 1960. The project called SETI, the Search for Extraterrestrial Intelligence, has been running with various degrees of funding and institutional support and public attention for more than 6 decades. And in those 6 decades, despite listening to hundreds of thousands of star systems, we have heard nothing conclusive, nothing undeniable, nothing that has forced a press conference where a NASA administrator stands up and says the words that would change everything. What we have heard is silence. Overwhelming, statistically expected, scientifically interpretable, but also emotionally heavy silence. There are many explanations for the silence. Some say that life is rarer than we think, that the emergence of intelligence from chemistry is so unlikely that even in a galaxy of 200 to 400 billion stars, it might have happened only once or twice or a handful of times. Some say that life is common but technological civilizations are self-destructive, that any species which develops the ability to communicate across interstellar distances also develops the ability to destroy itself, and most of them do. Some say that spacefaring civilizations simply don't broadcast in ways we can detect. Some say they broadcast, but we've been listening on the wrong frequencies with the wrong instruments at the wrong times. Frank Drake, the founder of modern SETI, formulated his famous equation in 1961. Start with the rate of star formation in the Milky Way. Multiply by the fraction of stars with planets. Multiply by the number of habitable planets per star system. Multiply by the fraction of habitable planets where life emerges. Multiply by the fraction of life-bearing planets where intelligence evolves. Multiply by the fraction of intelligent civilizations that develop detectable technology. Multiply by the average lifespan of such a civilization. The result is n, the number of detectable civilizations in the Milky Way right now. Drake himself, at the first SETI conference, estimated n at around 10. Carl Sagan was more optimistic. Some modern estimates, armed with Kepler and TESS exoplanet data, suggest that habitable worlds are so common that even if only 1 in a million of them produced life, there should be thousands of civilizations in our galaxy today. And yet, silence. 3I/Atlas does not break that silence. It doesn't claim to. Its radio signatures are absent. Its behavior, in most respects, is consistent with natural processes. But it opens a different kind of window, not into the question of whether other civilizations are broadcasting, but into the question of whether the universe, through the simple physical process of planetary system formation and gravitational ejection, is already mixing itself up. Already shuffling material from one stellar environment to another. Already doing, through purely natural mechanisms, something that resembles, without being, communication. The idea of the galaxy as an ecology, a connected system of interacting parts, is not common in popular science writing, but it is beginning to make inroads into serious astrophysics. The traditional picture of solar systems is one of isolation. Your solar system is your solar system. Its chemistry is shaped by the local stellar neighborhood at the time of formation, by the specific composition of the molecular cloud that collapsed to form it. What happens next door, in astronomical terms, is largely irrelevant. Stars don't talk to each other. Planets don't visit other planets. Systems are islands. But this picture was always a simplification, and observations like 3I/Atlas are making it impossible to sustain even as a useful approximation. Stars interact through gravitational flyby encounters. Not collisions, the distances are too vast, but close enough passes to perturb each other's Oort clouds, shaking loose comets and sending them into new trajectories. Molecular clouds are shared between stellar neighborhoods. Stellar winds from massive stars affect the chemistry of surrounding star-forming regions. And now, most concretely, we know that comets are ejected from planetary systems at a rate that means the interstellar medium is filled with them. Billions of them, perhaps trillions. If you filled the space between stars with enough comets, and the evidence increasingly suggests that the density is quite high, then the average comet in the Milky Way has, over the galaxy's lifetime, passed through multiple stellar systems. Not our solar system, not any specific system, but through the gravitational zones of various stars. Picking up some material here, losing some material there, being altered slightly by each interaction. 3I/Atlas, on its way to our solar system, had a very specific chemical fingerprint set 10 to 12 billion years ago. But its surface has been altered by cosmic radiation for that entire time. And during its perihelion passage, our sun's energy was sublimating its surface layer, exposing fresher material, creating chemistry that hadn't existed until that moment. When it leaves, it will carry that new chemistry with it. It is a carrier, a transport, a vector for molecular exchange between stellar systems, operating on billion-year timescales. Whether this transport has ever carried anything biological, whether it has ever moved life, not just chemistry, is a question we cannot answer. But the transport mechanism is real. We have watched it happen. In our sky, in our solar system, in the 8 months between July 2025 and March 2026. Let's slow down and think about the human experience of this event. Not the scientific experience, the human one. In the summer of 2025, somewhere in the world, there were children who looked up at the news and learned that a comet from another star was crossing our sky. This was not a story about asteroids hitting the Earth. This was not a story about climate change or politics or disease. This was a story about something being here, in our solar system, from somewhere else. Something old. Something alien in the most literal sense of the word, foreign, other, not of this place. And I wonder what those children thought. I wonder if any of them will remember it the way some people of an earlier generation remember the moon landing, or the moment they first saw images from the Hubble Space Telescope, or the night they read about Voyager 1 crossing the heliopause. That specific feeling of the sky suddenly becoming larger than it was before. Of the universe inserting itself into everyday life with an intimacy that feels almost like a tap on the shoulder. Look at this. I'm here. Notice me. There is a specific flavor of wonder that comes from interstellar objects. Not the wonder of a beautiful nebula, which is distant and static and safe. Not the wonder of an exoplanet, which is detected as a shadow in a light curve and is abstract in its existence. The wonder of an interstellar object is different. It is the wonder of proximity, of presence, of something from an incomprehensible distance being, right now, at a specific position in space that you can point a telescope at and see with the same instruments you use to look at Saturn or Mars. 3I/Atlas was here, not metaphorically, not in the way that a radio signal from a distant galaxy is here in the sense of being received. Physically here, moving through the three-dimensional space of our solar system, interacting with our sun's gravity, being photographed by our orbiting spacecraft. Its chemistry recorded in the silicon detectors of the most sophisticated telescope humanity has ever launched. And then it was gone. The temporariness of it, the irreversibility, is part of what gives this story its particular emotional texture. We will not get 3I/Atlas back. Not in a million years. Not in a billion. Its hyperbolic trajectory ensures that. Came once, and it is going, and the universe does not offer second chances on a timescale that means anything to a civilization that has existed for 300,000 years. Which is one of the reasons that the missed opportunity, the absence of a dedicated mission, the fact that we watched it from afar with instruments not designed for it, feels not just like a scientific failure but like something more personal. A version of the experience of watching something extraordinary unfold from too great a distance, knowing that if you were only closer you could touch it, and knowing that you will never have this particular chance again. The universe is not cruel. It doesn't withhold things out of malice. It simply is what it is, and what it is includes the occasional passage of a 10-billion-year-old traveler through our solar system at a speed that is double what our fastest rockets can achieve, on a trajectory that gives us 8 months of warning and no spacecraft on standby. We are not ready, but we were here. We looked. That is something. Now I want to explore something that isn't often addressed in the scientific literature about interstellar objects, but that I think is fundamental to understanding why this story matters to people who don't work in astronomy. The question of what interstellar objects mean for our understanding of our own origins. You have probably heard the phrase, "We are made of star stuff." It's one of Carl Sagan's most famous lines, drawn from his Cosmos series, and it is scientifically accurate. The carbon in your cells was forged in the nuclear furnaces of dying stars. The iron in your blood was created in a supernova explosion. The oxygen you breathe was produced in stellar interiors over billions of years of galactic chemistry. In a very real, literally true sense, your body is assembled from the ash of dead stars. But the story of our origins is more complicated than even that elegant formulation captures. Because the gas cloud that collapsed to form our solar system was not pristine. It had been already processed, already churned by supernovae and stellar winds and the passage of other molecular clouds and the cosmic ray bombardment of interstellar space. The material that became the Earth carried within it the history of many stellar generations. Not just our stellar neighborhood's history, but the Milky Way's. And now we know that comets, including comets from other stellar systems, have been transiting the galaxy for as long as there have been stellar systems, which means that the molecular cloud that became our solar system might have received contributions from interstellar comets. Chemistry from other systems, long dissolved into the cloud before our sun ever ignited. There is no way to know this directly. The record has been lost. The chemistry of the early solar system has been processed and reprocessed over 4.6 billion years. We cannot look at our own comets or at Earth's crust or at meteorites and see a distinct isotopic signature from an ancient interstellar visitor the way we can look at 3I/Atlas and see its alien fingerprint. But the possibility is real. The mechanism is real. We have just watched it happen. A comet from the early Milky Way passed through our solar system, sublimated material into the solar wind, and that material, some fraction of it, however tiny, has been incorporated into the ongoing chemistry of this system. Not in a way we'll ever be able to trace, but in a way that is physically real. The borders of our solar system are not walls. They are permeable membranes. And the universe, over billions of years, has been quietly moving molecules across them. Now let's talk about something that was barely discussed in the public coverage of 3I/Atlas, but that will shape the next chapter of the story more than anything else. What happens when we find the next one? Because we will find the next one. This is no longer a question. The detection infrastructure is in place. The Atlas network is operational. The Vera Rubin Observatory, whose LSST survey will image the entire accessible sky every few nights with extraordinary depth and sensitivity, is in the process of coming online. The pipeline for identifying interstellar objects, the mathematical tools, the community of astronomers who know what to look for, the institutional response infrastructure, all of it now exists in a way it didn't in 2017 when Oumuamua surprised everyone. The question is not whether we will detect more interstellar objects. The question is what we will do when we do. Avi Loeb has argued specifically and repeatedly for a coordinated scientific response. A standing mission capability, pre-deployed spacecraft, a rapid response protocol that can be triggered within weeks of a discovery announcement. Not unlike the planetary defense infrastructure that exists for asteroid threats, except aimed not at deflection but at rendezvous. The study, at the kind of close-up observation that would let us read an interstellar comet the way 3I/Atlas deserved to be read. Up close with the right instruments, for long enough to answer the real questions. The engineering challenges are real. An interstellar object moving at 58 kilometers per second relative to the Sun is not easily interceptable. To rendezvous, to actually match velocity and fly alongside rather than doing a high-speed flyby, requires either catching it early, when it is still far out and hasn't yet been accelerated much by the Sun's gravity, or using advanced propulsion technology. The solar Oberth maneuver, swinging very close to the Sun to gain a huge velocity boost before heading out to intercept, is one proposed approach. It requires a spacecraft that can survive very close solar approach, which is possible but demanding. Solar sails, nuclear propulsion, ion drives, all of these have been discussed as potential propulsion options for an interstellar object interceptor. None of this is science fiction. All of it is, in principle, feasible with technology we either have or could develop within a decade. The question is will. The question is whether the experience of 3I/Atlas is vivid enough, and the scientific case compelling enough, to move the needle on priorities and funding in a field that is perpetually constrained by what governments and agencies are willing to invest. Here is the argument for taking it seriously. These objects are physical samples from other solar systems. Every solar system that has ever existed has shed comets. Those comets have been traveling through the galaxy for billions of years. The interstellar medium, the space between stars, is, in effect, a library of chemistry from every planetary system that has ever formed in the Milky Way. And we are sitting at one star's address with instruments that can read that library if we build the capability to do so, watching the books fly by. The cost of not doing this is not abstract. It is the specific, nameable, innumerable loss of information about the universe that we will never get another opportunity to collect. The information about how planetary systems form, about the chemistry of the early galaxy, about how organic molecules are distributed, about whether the building blocks of life are widespread or local, about whether, at the extremes of probability, something more than chemistry ever hitched a ride on one of these ancient travelers. We are at the beginning of the interstellar object era. The era of Oumuamua and Borisov and 3I/Atlas was the era of first notice, of improvised observation, of realizing the phenomenon is real and significant. The next era, the era we are now entering, should be the era of readiness, of interceptors, of sample return, of the kind of direct, up-close study that would let us actually know what we are dealing with. We owe that to 3I/Atlas. Not because of what it might be, but because of what it definitely is. A messenger from the early universe, a sample of an ancient planetary system, a piece of evidence about the chemical diversity of the Milky Way that we have never had access to before. It deserves better than distant photographs. The next one will, if we choose to be ready. Let's spend some time with the science of what happens to an interstellar comet during its solar encounter. Because one of the things that makes 3I/Atlas scientifically extraordinary is not just what it is, but what happened to it while it was here. The encounter between this ancient, cold, interstellar body and the heat and radiation of our sun was a kind of experiment, the universe's experiment, and we had front-row seats to watch it run. When 3I/Atlas was still far out, beyond the orbit of Jupiter, the temperatures at its surface were extraordinarily low. Sunlight at that distance is very weak, about 4% of the intensity at Earth's distance. The surface of the nucleus, insulated by its thick radiation process crust, was below 100 Kelvin, minus 173 degrees Celsius. In those conditions, only the most volatile species, carbon monoxide, for instance, which sublimates at around 25 Kelvin in vacuum, should have been actively outgassing. And yet, the JWST observations from August 2025 showed significant carbon dioxide emission, far more than CO activity. This was already unusual. CO2 has a much higher sublimation temperature than CO. At the distances where 3I/Atlas was observed by JWST, solar heating should barely have reached the CO2 sublimation point. The explanation that most planetary scientists have converged on involves the structure of the crust. Over 10 billion years of cosmic ray bombardment, the outer layers of 3I/Atlas's nucleus may have developed what is called an irradiation mantle, a layer of complex organic polymers, created when radiation breaks apart simpler molecules and recombines them into larger, stickier structures. This layer is darker than pristine ice, which is why comets are much darker than you might expect. They're covered in organic gunk rather than clean, bright ice. It's structurally different from the ice beneath, and it has very different thermal properties. In this model, what drives the extraordinary CO2 activity at large distances is not that the solar heating is reaching the CO2 layer of the nucleus. It's that the CO2 is concentrated in or near the irradiation mantle itself, at or near the surface, where even modest solar heating is enough to sublimate it. Meanwhile, the water ice is buried deep beneath the crust, insulated from the sun's heat, suppressed. As the comet approaches the sun and the heating intensifies, the crust starts to break down in places. The irradiation mantle that took 10 billion years to build gets destroyed by solar radiation in a matter of months, at least in the most sun-exposed regions. Fresh surface is exposed. New volatiles become accessible. And this is exactly what the SphereX observations in December 2025 showed. A sudden increase in water activity, much stronger than the pre-perihelion readings, suggesting that the perihelion encounter had stripped some of the crust and exposed the water ice below. In other words, the sun spent several months doing to 3I/Atlas what cosmic ray bombardment spent 10 billion years building. And we watched it happen in real time in our own solar system, with instruments sensitive enough to detect the chemical evolution at each stage of the process. This is not just scientifically interesting, it is scientifically foundational, because 3I/Atlas represents the only direct observation we have of the surface chemistry and thermal behavior of a comet from the early Milky Way. Every other piece of evidence we have about the chemical composition of early planetary systems is indirect. It comes from reading stellar spectra, from modeling planetary formation, from inferring what conditions must have been like based on theoretical physics. 3I/Atlas handed us a sample, a physical object, chemistry we could measure directly, and it will take years to fully process what that sample is telling us about the early galaxy. There is something I find deeply strange and deeply human about the fact that we named it 3I/Atlas. 3I for third interstellar, Atlas for the telescope that found it. Functional, descriptive, precise. The kind of name you give something when you are a scientific community that processes thousands of new objects every year and needs a system that scales. You can't name every asteroid something poetic. You'd run out of names. So you use codes, designators, letters and numbers that mean something in context. But consider, this object has been traveling through the galaxy for 10 to 12 billion years. It has crossed distances that are genuinely incomprehensible. The scale of what it has seen, if seen means anything for an unconscious rock, is so far beyond our experience that language begins to fail. And we name it 3I/Atlas. Not because the name is bad. It's a good name as scientific names go. But because there is something in that gap between the cosmic scale of the object and the clinical precision of the human designation that is simultaneously funny and poignant and deeply characteristic of us. We build the instruments to detect it. We analyze the data. We argue about its jets on Twitter and publish papers on its isotopes and estimate its age with 2 independent methods. And then we file it under a code that tells you it's the third one and who found it. Oumuamua at least got a Hawaiian name. scout, messenger, something that carried the weight of what it was. 3I/Atlas will probably always be 3I/Atlas in the scientific literature. And somehow that feels right too. We are a species of taxonomists as much as we are a species of poets. We label because we want to understand, and understanding something means being able to refer to it precisely. But the label doesn't contain the thing. The thing is 10 billion years old, half a kilometer across, made of ice and rock and ancient chemistry, and it sailed through our solar system and is never coming back. No label touches that. No paper captures it. Not even this one. I want to return to the question of the anomalies one more time, because I don't think I've been fully fair to the complexity of what is actually being debated in the scientific community. There are not two camps, the believers and the skeptics, the alien hunters and the cometary conservatives. There are dozens of positions, distributed across a spectrum of interpretive caution, and most serious scientists occupy a genuinely middle ground that the popular coverage of this story tended to flatten. The majority view, well represented by planetary scientists, comet specialists, and solar system dynamicists, goes roughly like this: 3I/Atlas is a comet. Its chemistry is unusual by the standards of our solar system, but our solar system is one data point in a galaxy with hundreds of billions of stars. We have no reason to expect interstellar comets to be chemically identical to local ones. The non-gravitational acceleration is explicable by outgassing. The jets are explicable by localized ice patches on a rotating nucleus. The anti-tail is explicable by large grain dynamics. The mass-budget discrepancy may resolve when we better understand the population of interstellar objects. The Hill-sphere coincidence is a numerical curiosity that happens to be there but doesn't demand an exotic explanation. Overall, extraordinary comet, natural, done. This view is held by most people who have spent their careers studying comets, and their expertise deserves weight. But there is a secondary view, held by a minority of serious scientists including Loeb and several of his collaborators, that goes like this: the cumulative improbability of the full suite of observations is higher than the mainstream acknowledges. The individual explanations for each anomaly are plausible but collectively require a level of special circumstance that would be considered, in other contexts, grounds for seeking a different explanation. The symmetric jets, the Hill-sphere flyby, the anti-tail behavior, the orbital alignment with the ecliptic, the arrival direction near the wow signal, these are not each alone strong evidence for anything. But they are each alone unlikely enough that their co-occurrence deserves more than a shrug. And the appropriate scientific response is not certainty in either direction, but more data, better missions, closer observation. This view deserves respect even when you disagree with specific calculations or specific claims. The underlying epistemological point, that cumulative improbability in a dataset deserves active investigation rather than passive explanation, is sound scientific reasoning. And there is a third view, less commonly expressed but worth naming, that the question of whether 3I/Atlas is natural or artificial is less important than the question of what the phenomenon of interstellar objects tells us about the galaxy, about planetary formation, about the distribution of chemistry, about the early universe. This view says, whether this particular object is a comet or a probe matters less than what the existence of detectable interstellar objects means for our understanding of the Milky Way as an interconnected system. And that regardless of the alien technology question, the scientific content of 3I/Atlas is so rich, so unique, so irreplaceable, that we are obligated to study it as carefully as possible and build the capacity to study the next one even more carefully. I find myself most sympathetic to this third view. Not because I don't care about the alien question, I do deeply, but because I think the alien question, as applied to 3I/Atlas, may be getting in the way of the science. The science is extraordinary. The galaxy ecology story, the ancient chemistry story, the first direct sample from the early Milky Way story, these are profound even if every single anomaly has a natural explanation. And if we let the argument about whether it might be alien consume all the oxygen in the room, we risk missing the scientific forest for the speculative trees. 3I/Atlas is, at minimum, the oldest material ever directly studied in the history of astronomy. At minimum, that alone is a statement of extraordinary scientific significance. Let me take you somewhere specific. Let's stand in the Atacama Desert on the night of July 1, 2025, and watch the moment of discovery happen from the inside. The telescope is automated. Nobody is standing at the eyepiece. That's not how modern survey astronomy works. The instrument is connected to servers. The servers process the images. The algorithms compare tonight's images to reference catalogs, flag moving objects, classify their motion, log them for human review. In the case of the Atlas network, the pipeline runs through the night and the flagged objects are reviewed the next morning by humans who look at the data and decide what matters. In the morning of July 2nd, somewhere in this pipeline, the dot that would become 3I/Atlas appeared in the flagged list. A moving object, position, velocity, preliminary orbit. And the preliminary orbit said, very hyperbolic. Within hours, the alert went out. Within hours more, follow-up observatories across the world were confirming. By the end of the day, the hyperbolic nature was beyond doubt. Who was the first human being to understand, in real time, that this was interstellar? We don't know. It was probably someone at a computer screen, running orbital calculations, watching the eccentricity come back greater than 1.0 and then running it again to make sure. It was probably not a dramatic moment. There was no orchestra, no dramatic lighting, no gathering of senior figures in a conference room to solemnly confirm what everyone already suspected. It was probably someone, alone at a desk, running the numbers, and then typing a message to a colleague, check this one, and the colleague checked it, and the numbers said, yes, this one is from somewhere else. That is how discovery actually happens. Not in the grand orchestrated moments that documentaries reconstruct. In the quiet, the dark, the ordinary work of people who have chosen to spend their professional lives looking for things that are not supposed to be there. And occasionally, if the universe is in a generous mood, the thing that is not supposed to be there is actually there. There is a philosophical concept that I keep returning to when I think about 3I/Atlas. It's called the overview effect. It was first named by Frank White in a 1987 book, drawing on the accounts of astronauts who described what it felt like to see Earth from space for the first time. The sudden, visceral, cognitive shift that comes from seeing your entire world, every human, every city, every ocean, every war, every love story, as a fragile marble hanging in the dark. The sense of the Earth as finite and precious and undivided by the lines we draw on maps. The humility that comes from perspective. 3I/Atlas produces, I think, a different version of the same effect. Not the overview effect of seeing Earth from space. Call it the interstellar effect. The cognitive shift that comes from holding in mind, at the same time, both the incomprehensible scale of what 3I/Atlas represents, 12 billion years of time, the chemical memory of the early Milky Way, a traveler from a dead solar system, a distance that makes even intergalactic astronomy feel cozy, and the fact that it passed through our sky in 2025 and we watched it. The scale reduction is dizzying. The universe is 93 billion light-years across. The Milky Way is 100,000 light-years across. The distance between our solar system and the nearest star is 4 light-years. And 3I/Atlas, which came from somewhere on the far side of that context, ended up visible in amateur telescopes from suburban backyards in North America and Europe. The same sky, the same dark, the same habit of looking up. That compression of scale, from the cosmic to the personal, is, I think, what gives interstellar objects their particular power over the imagination. They are evidence that the universe is not organized in the neat, separate, hierarchical way we sometimes think. Galaxies, clusters, filaments, voids, yes, the large-scale structure is real. But nested inside it, at every scale, there is exchange. There is mixing. There is continuity. The chemistry of the early universe finds its way, through the random walks of interstellar comets, to the neighborhood of stars that formed billions of years later. The ancient finds the recent. The distant finds the near. We are not separate from the rest of the galaxy. We are connected to it in ways that are physical and chemical and genuinely meaningful. The same atoms that 3I/Atlas was carrying through the early Milky Way are here, in our solar system, in quantities that can't be directly measured but that cannot be zero. Every time an interstellar comet passes through a solar system, it deposits some material. It absorbs some material. Over the billions of years during which the solar system has existed, dozens of interstellar comets must have passed through, some perhaps much more closely than 3I/Atlas. some perhaps at much higher speeds. Some perhaps during the early phase of solar system formation when the disk was still present and interactions would have been much richer. We are, in a very real sense, partly made of the galaxy, not just of our own stellar neighborhood, of the whole thing, of comets from systems we will never visit, from stars that are dead, from times we cannot imagine. The same iron in your blood has a stellar history, yes, but it has also, possibly, an interstellar transport history. Chemistry carried across the void on bodies like 3I/Atlas, over timescales that make the word long meaningless. This is speculative. I know it's speculative, but it is the kind of speculation that becomes less speculative with every interstellar object we detect, because each one shows us the mechanism operating in real time. The mechanism is real. The question of scale, how much, how often, over what distances, with what chemical consequences, is open. But the mechanism is real, and that, for me, is the deepest truth of 3I/Atlas. Not the anomalies, not the jets, not the wow signal coincidence, but the simple, physical, demonstrated fact that the galaxy moves material between stars. That the universe is not a collection of isolated islands, but something more like an ocean. And that this comet, this 10-billion-year-old half-kilometer piece of ice and rock and ancient chemistry, was a wave in that ocean, passing through our harbor briefly and gone. Now, as we settle into the quiet of this moment, I want to bring you back to where we started. Back to the dark. Back to the thought of something moving through it right now while you breathe. 3I/Atlas is past Jupiter. The gravitational encounter is over. Whatever the Perekove distance ultimately measured, whether it precisely matched the hill radius or fell slightly inside or outside, the physics played out and the comet continued on its hyperbolic path. The JPL tracking data is being updated as we speak, as the last few astrometric measurements from Earth's largest telescopes come in before the comet fades beyond their reach. In the coming months, it will pass the orbit of Saturn. Moving at 28 kilometers per second at this distance, it takes approximately 6 months to travel each additional astronomical unit. By the end of 2026, it will be approaching Uranus's orbital distance, though not near Uranus itself. The comet is heading in a different direction, away from the ecliptic plane, out of the solar system in a trajectory that passes roughly through the region of the sky near the constellation Gemini. By 2028, it will be beyond Uranus. By 2031, beyond Neptune. By 2035, it will be in the Kuiper Belt's outer regions, approaching the heliopause. By 2040, it will have crossed into true interstellar space, beyond the heliosphere into the thin, cold medium between stars, where the sun's solar wind no longer dominates and the magnetic field of our star gives way to the galactic magnetic field. At that point, 3I/Atlas will be undetectable by any instrument we currently possess. The Voyager probes, our farthest ranging emissaries, launched in 1977 and still operational almost 50 years later, are only about 23 billion kilometers from the Sun. At 3I/Atlas's speed, the comet will have passed that distance by the early 2030s. After that, it is beyond even the most extreme limits of our current technology. Gone. Truly, finally, irreversibly gone. Not into nothingness. Into the galaxy. Into the three-dimensional space of the Milky Way, where it will continue its journey for the next 10 billion years. It will pass through molecular clouds. It will occasionally approach other stars. It will cross spiral arms. It will outlive most of the stars currently in the sky. It may, over timescales that make all of human history look like an instant, pass through other solar systems. Be observed, perhaps, by other creatures on other worlds with other instruments, asking the same questions we asked. Or not. The galaxy is mostly empty. Most interstellar objects pass through most of it without encountering anything of note. The odds of any specific comet making a close approach to any specific star in any given billion years are very small. But the odds are not zero, and 10 billion years is a long time. 3I/Atlas has time. It is, in a very real sense, just getting started. The last image of 3I/Atlas that I'm aware of, taken by a small amateur telescope in Italy on March 11, 2026, shows it as a faint, slightly fuzzy point against the background stars. Magnitude around 18. Barely detectable. A smudge of light produced by 10 exposures of 120 seconds each. stacked and processed to squeeze out as much signal as possible. The field of view is filled with stars. The comet is just another dot, distinguishable from the rest only because it has moved between exposures. The astronomer who took that image is named Tony Scarmato. He has been one of the most dedicated observers of 3I/Atlas throughout its solar system passage, contributing astrometry and photometry and image processing throughout the encounter. He is not a professional astronomer. He is an amateur, equipped with a 25-centimeter telescope and enough knowledge of image processing to extract science from modest equipment. That image, that last visible trace of an interstellar comet from the early Milky Way, captured by a private citizen with a backyard telescope in southern Europe, is, to me, one of the most moving artifacts of this entire story. Not because of its scientific content, because of what it represents. A human being, in the year 2026, looking at something that formed before the Earth existed, and capturing the final visible evidence of its presence in our solar system. The telescope is not sophisticated by professional standards, but it was pointed in the right direction. It was tracking. It was accumulating light from something 10 billion years old. And the image shows what it shows. A tiny, fading spot, moving slowly toward the edge of the solar system, carrying its secrets with it. That image will outlast the comet's visibility. It will be in archives long after 3I/Atlas has passed beyond the reach of every instrument ever built. And decades from now, when we have better missions and better understanding and perhaps even direct samples from interstellar objects, someone will pull up that image of a small fuzzy dot in a field of stars and remember what it felt like to watch something extraordinary leave. And so we arrive at the end. Not the end of the science that continues in papers that will be published for years, in the JUICE data that is still being analyzed, in the Hubble monitoring program that tracked 3I/Atlas through early 2026. Not the end of the mystery. Some of the anomalies remain unexplained and may remain so. Not the end of the search. The Vera Rubin Observatory is beginning to transform our ability to detect interstellar objects, and the next discovery may be months away. But the end of 3I/Atlas itself in our sky. The end of this particular visitor's particular passage. The closing of this specific window. What do we take away? We take away the science. The age, 10 to 12 billion years, from a JWST measurement that represents one of the most sophisticated observational results in the history of astronomy. The chemistry, unusually rich in CO2, deuterium-heavy water, ancient organic molecules. A composition unlike anything in our solar system. The behavior, jets that persisted and evolved and baffled some of the best comet specialists in the world. The brightness excesses. The isotopic story. The physical evidence that the early Milky Way made comets with chemistry dramatically different from our own. We take away the lesson in humility. Not the cosmic kind, not the overview effect humility of seeing Earth as a pale blue dot. The specific, practical, programmatic humility of recognizing that we were not ready. That we had the instruments to detect this object and study it from afar, but not to study it properly. And that this gap between what we could do and what we needed to do is a gap that has a name and a price tag and a technical solution if we choose to invest in it. We take away the reminder that science is not finished. That we've explained it is not the same as we understand it. That the job of an anomaly is not to be explained away but to be genuinely resolved, with data, with missions, with the intellectual honesty to keep asking the question until the answer is actually clear. And we take away something harder to name, a feeling more than a fact. The feeling of having been in the presence of something vast and old and indifferent, and of having measured it with tiny instruments and sharp minds, and of having extracted from its passage through our sky a set of numbers and images and spectra that represent, in a real sense, the best we can do right now. Not the best we could ever do. Not the best we will do. But the best we did today with what we had. That is enough. Not in the sense that it should satisfy us, it shouldn't. In the sense that it is what we have. The data is there. The papers are being written. The science is real. And the next interstellar object is already on its way. We don't know when it will arrive. We don't know where it will come from. We don't know if it will show us the same anomalies, different anomalies, or none at all. We don't know if it will be smaller or larger, faster or slower, older or newer. We don't know if the next one will answer the question that 3i/Atlas left open, or deepen it. What we know is that it's coming, and that when it arrives, we will look. We will always look. That is what we do. So go to sleep now if you're listening to this in the dark. Go to sleep knowing that somewhere out there, beyond Jupiter, past Saturn's orbit, heading for the edge of everything we can reach, something from before the Earth existed is still moving, still carrying its chemistry, still following the hyperbolic path that physics laid out for it 12 billion years ago, modified only slightly by the brief passage through our small corner of the galaxy. It is gone from our sight, but not from our knowledge, not from our data, not from the 12 papers already published and the 40 more in preparation and the databases that will hold the astrometry and the photometry and the spectroscopy for as long as we have computers to store it. We saw it. We measured it. We argued about it. We missed the chance to touch it, but we never looked away. And in the morning, we will build the next telescope, write the next proposal, design the next interceptor, train the next generation of astronomers who will be in their seats when the fourth interstellar object crosses the line of Jupiter's orbit and a new automated flag lights up on a new screen and someone, again, checks the numbers and runs them again and then sends the message. Check this one. We are a young species with ancient instruments, staring at a galaxy that has been going on without us for most of its life. We arrived late. We have been paying attention for a fraction of an eye blink in cosmic time. And in that fraction of an eye blink, we detected 3 messengers from beyond our solar system, analyzed their chemistry, dated their birth, argued about their nature, and began, slowly, imperfectly, but actually, to understand the galaxy we live in. That is not nothing. That is, in the long run of things, everything. Sleep well. End of extended sections. Part 3. Insert between Part 2 sections. Here is something that rarely makes it into the press releases. Something that the official NASA fact sheets don't dwell on, because fact sheets deal in confirmed data rather than the texture of how science actually feels from inside the process. The scientists who were studying 3i/Atlas were scared. Not of the comet. There was never any physical threat, it was always going to pass well clear of Earth, and the orbital mechanics were never in question on that score. They were scared of something more subtle and more professionally consequential. They were scared of being wrong. Comet science is a field with a long history and a very specific culture. You have to be careful with comets. They are notoriously unpredictable. They outburst. They split. They fade faster than expected or brighten 20 times more than the models say they should. The community has been burned before by comets that were supposed to be the comet of the century and fizzled out, by predictions that didn't pan out, by speculative papers that embarrassed their authors. And so there is, in the comet science community, a certain epistemic caution, preference for hedged language, a resistance to extraordinary claims. And then 3i/Atlas comes along, and it keeps doing things that are hard to explain, and the community has to navigate between 2 failure modes simultaneously. One failure mode is overclaiming, publishing papers that attribute anomalies to alien technology when the evidence doesn't support that conclusion, embarrassing the field, inviting ridicule. The other failure mode is underclaiming, explaining everything away too quickly, missing something genuinely important, being the scientists who were so careful not to be the alien guys that they missed the actual story. Both of these failure modes have real career costs. Both of them have been instantiated in various astronomical debates, with named scientists on both sides. And with 3i/Atlas, the scientific community had to walk a line that was unusually narrow and unusually public, because this object attracted a level of media attention that brought everyone's positions into the spotlight. I watched this dynamic play out in the papers and the social media threads and the conference talks and the public statements throughout 2025 and 2026. And what struck me was not the disagreements. Those were predictable and productive, but the earnestness. The genuine, obvious, sometimes almost desperate earnestness of scientists who wanted to understand this thing correctly. Not to be famous, not to be right, but to actually know what it was. That earnestness, in the context of an object that may represent the most scientifically significant visitor to our solar system in recorded history, was its own kind of beautiful thing. Let's talk about something that we haven't addressed yet. What it would mean, practically and scientifically, if some of the anomalies could not ultimately be resolved by natural explanations. I want to be very careful here because this is territory where speculation runs ahead of data very easily, and where the history of science warns us to be cautious. The history of astronomy is full of anomalies that were initially considered exotic and turned out to have mundane explanations. The advance of Mercury's perihelion was once a mystery and became evidence for general relativity, not alien engineering. The face on Mars turned out to be a low-resolution artifact. Many early SETI candidates turned out to be rotating neutron stars or atmospheric interference. The principle of parsimony, Occam's razor, is a good guide for a reason. The simplest explanation consistent with the data is usually correct, but usually is not always. And the history of science also includes cases where the anomaly was real and the conventional explanation was wrong, where the experts were defending a framework that needed updating, where the instinct to preserve the existing model led to a delay in accepting a better one. Continental drift was dismissed for decades before plate tectonics became orthodoxy. The Big Bang was resisted by a generation of steady-state cosmologists. Helicobacter pylori was laughed out of medical conferences before Barry Marshall drank a petri dish of the bacteria to prove his point and won the Nobel Prize. So when Avi Loeb says that the cumulative improbability of 3I/Atlas's anomalies deserves more than dismissal, he is making a point with precedent. Not because any specific anomaly demands an artificial explanation, but because the epistemological point that extraordinary patterns deserve extraordinary investigation, not just extraordinary explanations, is sound. What would it mean if we accepted, even provisionally, the possibility that something in 3I/Atlas's behavior was intentional? Not that it is alien, but that the possibility is real enough to warrant specific, targeted tests. It would mean deploying the next available spacecraft to a close flyby of the next interstellar object, specifically to check for signatures of artificial construction. High-resolution imaging, mass spectrometry at the nucleus, radar tomography to probe the interior structure, measurements looking for regular, repetitive, geometry-based structures in the nucleus that would be unlikely to arise from natural accretion. None of this is exotic technology. All of it is things we do with planetary missions. The difference is prioritization and purpose. Specifically designing a mission with the hypothesis, this might not be natural as a target test case, rather than assuming naturalism from the outset. The return on that investment, even in the overwhelming probability that the result is confirmed natural object, here's the chemistry, is enormous. Because we would also get exactly the same science we would get from any other close interstellar object mission. The physics of the nucleus, the chemistry of the ice, the structure of the coma, the rate of outgassing, all of it at close range directly measured. And if, in the extraordinary scenario that Loeb and others consider worth testing, the imaging revealed something unexpected, some geometry, some regularity, some structure that nature doesn't build, well, that would be a different conversation, a much larger one, a civilization reshaping one. The cost of testing the hypothesis is build the mission. The cost of not testing it is we never find out. Let me spend some time with the chemistry because I think it deserves more attention than it typically gets in the popular coverage of this story, which tends to focus on the jets and the anomalies and the potential alien connection. The chemistry of 3I/Atlas is, independent of all those questions, among the most scientifically significant data we have obtained in the past decade. And here's why. Every time we look at our own solar system's comets, we are looking at chemistry from one specific moment in time and one specific location in the galaxy. The Oort cloud comets, the Jupiter family comets, the short-period comets, they all formed in the same molecular cloud that became our solar system roughly 4.6 billion years ago, in the thin disk of a middle-aged spiral galaxy. They reflect the chemistry of our neighborhood, our era. We have exactly one data point. 3I/Atlas gives us a second data point. And that second data point is from a completely different moment in cosmic history, the early universe, when the Milky Way was being assembled from the first generation of stars. The chemistry is different. The isotopes are different. The CO2 to water ratio is inverted. The deuterium content is off the charts by local standards. The nickel to iron ratio was anomalous in the early stages of the encounter. All of this tells us something we genuinely did not know before July 2025. The chemical diversity of comets across the galaxy is much larger than our local sample suggested. The comets we have been using as benchmarks, as typical comets, are actually just our local comets. They represent one flavor in what appears to be a much richer variety. This matters for astrobiology, because astrobiologists use cometary chemistry as a proxy for the distribution of organic molecules across the galaxy. If we have been assuming that all comets everywhere look more or less like our solar system's comets, we have been wrong. The range is wider. The distribution of CO2-rich versus water-rich objects may vary dramatically with the age and metallicity of the parent stellar population. And it matters for planetary formation theory, because the models we use to understand how planets form around stars, including how habitable worlds like Earth are built, rely on knowing what the building blocks look like. If the building blocks in the early galaxy were chemically different from what we see locally, the planets that formed then may have had different compositions, different volatile inventories, different surfaces, which affects habitability, which affects the question of where and when in cosmic history life could have emerged. The JWST result, that 3I/Atlas has a deuterium to hydrogen ratio more than 10 times higher than any solar system comet, is particularly striking in this context. That ratio in comets has long been compared to the ratio in Earth's oceans, in an effort to understand where Earth's water came from. Our oceans have a D/H ratio of 0.015%. Solar system comets range from roughly 0.01 to 0.06%. The match and the mismatch between cometary water and ocean water has been used to argue about how much of Earth's water was delivered by comets versus other sources. 3I/Atlas's water would not be the source of Earth's oceans. Its D/H ratio of 0.95% is wildly off from Earth's. But it tells us that ancient comets from the early galaxy had dramatically different water chemistry, which tells us that planets forming around early galaxy stars may have received water with a very different isotopic signature, which tells us that the bulk hydrogen chemistry of those worlds, including any oceans they might have developed, was different from ours. Not better or worse, different. Another data point in the space of possible worlds. We have exactly 2 interstellar comets with measured chemistry, 2I/Borisov and 3I/Atlas. Borisov looked similar to our solar system's comets. 3I/Atlas looks completely different. 2 data points. The range of the distribution is already enormous. The next interstellar object will add a 3rd data point. Over the decades ahead, as the Vera Rubin Observatory brings us dozens more, the distribution will fill in. And we will begin to understand not just our own solar system, but the population of planetary systems across the galaxy through the chemistry of their debris. That is a scientific revolution in slow motion. And it started in July 2025 with a fuzzy dot on a telescope image in Chile. There is one more dimension of this story that I want to explore before we come to rest, because I think it is underappreciated and deeply important. It's the dimension of time, not the age of the object, which we've addressed in detail, but the time dimension of our detection capability itself. We have been capable of detecting interstellar objects passing through our solar system for approximately 10 years. The technology, the survey depth, the automated algorithms, the rapid follow-up pipelines, all of this only came together in the mid-2010s, just before Oumuamua arrived in 2017. Before that, we would not have recognized it as interstellar even if it had been imaged. The analysis would have been ambiguous or missed entirely. In cosmological terms, 10 years is nothing. It is an instant. It is a rounding error. But in that 10-year instant, we have found 3 interstellar objects. 3. In 10 years, in a solar system that occupies a vanishingly small fraction of the galaxy's volume, during a survey that covers only a portion of the sky at a time. The implication of finding 3 objects in 10 years, extrapolating from the volume of space actually surveyed and the completeness of the detection, is that the interstellar medium is full of objects like this. Estimates vary, but some calculations suggest there are between 1 and 10 interstellar objects per cubic astronomical unit in the neighborhood of our solar system at any given time, which means at any moment, there are hundreds or thousands of interstellar objects transiting through the volume of our solar system, from inside the orbit of Jupiter to the heliopause, undetected, moving through our neighborhood, Objects from other solar systems, some ancient, some recent, some large, some tiny. All of them invisible to us because our survey capability, even now, can only catch a fraction. The universe has been sending messengers through our solar system for billions of years. We have been capable of reading them for 10. Think about what we might have missed. Not in the sense of lost data, we couldn't have gotten it, we didn't have the tools, but in the sense of scale. If there are 1 to 10 interstellar objects per cubic astronomical unit in the solar neighborhood, and if this density has been roughly constant over geological time, then our solar system has been receiving these visitors at a constant rate for its entire history. Billions of interstellar objects, each carrying chemistry from another star system, have passed through the volume of our solar system while the Earth formed, while life emerged, while the first cells learned to divide, while animals appeared, while we evolved. We notice 3. There is something both humbling and exciting about this picture. Humbling because it means we have been swimming in a sea of interstellar chemistry for our entire existence without knowing it. Exciting because it means the sea is there. The exchange is real. The galaxy is an ecology in a way that is physical and chemical and happening all the time, not as metaphor but as literal molecular transport. And every improvement in our detection capability, every new telescope, every better algorithm, every dedicated survey mission, brings more of this picture into focus. What we see now is a suggestion, a hint, a glimpse of the edge of something much larger. What future astronomers will see, equipped with the facilities we are beginning to build, is the full picture. They will have a catalog. Dozens of interstellar objects with measured chemistry, orbital histories, age estimates, structural analyses. They will be able to map the chemical diversity of the galactic disk over billions of years of history, using these ancient messengers as samples. They will be able to compare the chemistry of objects from different galactic populations, from different stellar metallicities, from different epochs of galactic history. They will understand the distribution of volatiles across the Milky Way in a way that is currently inaccessible to us. And 3I/Atlas will be the second entry in that catalog. Data point number 2. The one with the ancient water and the CO2-dominated coma and the anomalous jets and the jets that never fully resolved. The one that prompted the construction of the Interceptor mission. The one that made the conversation about readiness impossible to avoid. I want to return briefly to the wow signal, not to make a claim about what it was or what it means, but to sit with the strangeness of it for a moment, because I think that strangeness is instructive. In 1977, a radio telescope received a signal, 72 seconds, strong, narrowband, near the hydrogen frequency, never seen again, no confirmed source, no explanation. In 2025, an interstellar object arrived from a direction within 9 degrees of where that signal came from. These two facts coexist. They are not connected, or at least we have no evidence they are connected, but they coexist. They are both in the historical record. And the fact that they coexist does something to the imagination that cannot be fully undone by the observation that 9 degrees is a lot and that coincidences happen. What it does is this: it reminds us that our knowledge is incomplete, that the universe has had 13.8 billion years to develop complexity, and we have had about 100 years to notice it, that the space between what we know and what exists is larger than the space between stars. The wow signal is, in this light, not primarily interesting as a potential technosignature. It is interesting as a symbol of that gap. A symbol of the fact that the universe has already sent us something we couldn't interpret, from a direction we couldn't pinpoint, on a frequency we happened to be listening to on a night when someone happened to be reading the printout. And that we have been trying to hear it again for almost 50 years and haven't. What if there are 100 wow signals in our data archives that nobody has checked? What if there are signals in frequency ranges we haven't systematically searched? What if the technosignature, when it comes, is not a radio signal at all but a pattern in the trajectory of a comet, or a specific spectral signature in the coma of an interstellar object, or something else entirely that falls outside the categories we're currently examining? These are not rhetorical questions. They are the actual questions that drive SETI research. And 3I/Atlas, by arriving from near the wow signal direction with an unusual behavioral profile, is a reminder that the answer might not come in the form we expect. That the universe is creative in its methods, and that waiting for a radio broadcast might miss the point. Avi Loeb has argued that the galaxy may contain interstellar probes, objects dispatched by technological civilizations to explore, or to carry information, or to seed chemistry, or simply to persist as evidence that civilization existed here and went somewhere. He argues that we should look for such objects the same way we look for any natural phenomenon. Systematically, with well-designed instruments, without prejudging what we will find. Most of his colleagues think this overreaches. They think the prior probability of encountering an alien probe in our solar system, among the billions of natural comets and asteroids, is so low that the resources required to search for it would be better spent elsewhere. They may be right. Probabilistically, they probably are right. But the counterargument is this: if a probe existed, and if it were designed to be detectable, what would it look like? It would look like a natural comet with unusual behavior. It would have a coma to blend in. It would have chemical signatures consistent with natural processes. But it would also have some residual anomalies, some behavior that a sufficiently attentive observer would notice that doesn't quite fit, that accumulates into a pattern of improbability. It would look, in other words, a bit like 3I/Atlas. This is not proof of anything. It is an observation about the structure of the problem. If alien probes are possible and real, they might be detectable precisely through the kind of anomaly cataloging that Loeb is doing. And if they are not real, the worst outcome of Loeb's approach is that we carefully analyze a natural comet and learn a great deal of astronomy. The best outcome of ignoring him, if he happens to be right, is something no one wants to contemplate. There is a specific kind of loneliness that comes from thinking too hard about the Fermi paradox. You've probably encountered it. The question goes, given the size and age of the universe, and the apparent abundance of conditions suitable for life, why do we see no evidence of other intelligent beings? It's called the Great Silence, or sometimes the Great Filter, the idea that there is some bottleneck in the development of civilizations that prevents them from becoming detectable on cosmic scales. Maybe the filter is behind us. The emergence of life or of intelligence is so unlikely that we are genuinely alone. Maybe the filter is ahead of us. Civilizations consistently self-destruct before reaching the stars. 3I/Atlas doesn't resolve the Fermi paradox, but it adds something to the texture of the problem that I find genuinely haunting. If interstellar objects transit our solar system continuously, at a rate of perhaps hundreds or thousands per year, and if a technological civilization wanted to make its presence known over interstellar distances in billions of years, the most reliable method might not be radio. Radio signals decay with distance. They are directional. They are detectable only if you happen to be pointing the right instrument at the right star at the right time and the right frequency. But a physical object, a probe or a probe-like artifact embedded in a comet, or simply a comet modified in some small but detectable way, travels at a constant velocity regardless of distance. It doesn't decay. It doesn't fade. It arrives physically in the target solar system. It can be seen with the same instruments you use to track asteroids. It carries its information in a form that is robust against the vagaries of radio noise and stellar interference. If you were a civilization trying to broadcast your existence not to your immediate neighbors but to the entire galaxy, over timescales of billions of years, without being able to know who is listening or where or when, physical objects might be your best option. Seeds in the cosmic wind, each one traveling independently, carrying the signature of its origin, drifting until gravity or chance or design brings it to another star. This is not the same as claiming 3I/Atlas is such an object. It is a thought experiment about the problem space of interstellar communication, about the ways in which physical chemistry and trajectory might encode information more robustly than electromagnetic signals, about the possibility that the library of interstellar objects is, in some sense, a library carrying encoded history from the systems that ejected them, readable by whoever develops the instruments to read it. The isotope data we got from 3I/Atlas is essentially exactly that: chemistry that encodes when and where the object formed. Not intentionally encoded in 3I/Atlas's case. The isotope ratios are a natural consequence of the physical conditions at formation, not a design signal. But the principle is there. Chemistry is a record. Physical objects carry their history in their molecules. And if a civilization wanted to leave a record that could persist for billions of years in a form that any sufficiently sophisticated observer could read, encoding it in the chemistry of physical objects is not obviously worse than encoding it in radio waves. We are doing exactly that ourselves, right now. The Pioneer plaques, bolted to Pioneer 10 and 11. The Voyager golden records, those extraordinary artifacts of optimism and ambition, carrying music and images and human voices on their endless journey into the interstellar dark. We are leaving physical records in the void because we understand, at some level, that physical records last. We are not sure anyone will ever find them. We are not sure it matters. But we do it anyway because we want to be known, and because knowledge is the thing we value most. 3I/Atlas is someone's pioneer plaque in the most literal sense, even if that someone is just physics and stellar dynamics rather than an intentional civilization. Carries its chemistry. Its record is readable. We read it, and the reading changed us, in the small ways that every genuine encounter with the unknown changes us. We know a little more. We are a little less certain of our models. We are a little more curious about what else is out there. We are a little more determined to be ready for the next one. That is not nothing. Let me sit with you in the dark for a moment longer before we come to the end of this. The dark is not empty. You know this now if you didn't before. The space between stars is full of travelers, ancient comets from dead systems, chunks of chemistry from the early universe, carriers of molecular cargo that have been moving between stellar neighborhoods since the galaxy was young. Not one, not 100, but billions of them, moving at tens of kilometers per second in every direction, on hyperbolic orbits that will never repeat, crossing the full scale of the Milky Way over the course of geological time. Most of them will never be detected. Most of them will pass through solar system after solar system without a single instrument noting their presence. They will arrive and depart and carry their chemistry into the void, and nobody will know. Not because nobody is watching, but because the scale of the galaxy is so vast, and the scale of any individual solar system is so small, that even the most dedicated survey of 1,000 solar systems would catch only a tiny fraction of the traffic. But occasionally, rarely, one of them will pass through a solar system where something has developed the capability to look, to see, to measure, to ask, where did you come from? What are you made of? How old are you? Where are you going? And the comet will answer in the only language it knows, chemistry, trajectories, jets, isotopes, the frozen memory of its birth, speaking to anyone patient enough to decode it. We decoded 3I/Atlas, imperfectly, from too far away, with instruments not designed for the purpose, in a rush because the window was closing. But we decoded it. We measured its age. We characterized its chemistry. We watched its jets. We tracked its path. And it tells us this: the galaxy is old and its chemistry is diverse, and objects travel between stellar systems, and the early universe made comets very different from the ones we see in our own solar system, and the universe is not a static, isolated, hierarchically organized collection of separate worlds, but a dynamic, interconnected, chemically active system in which material migrates and mixes and carries records across distances and timescales that beggar the imagination. That is what 3I/Atlas says. In the language of isotopes and carbon ratios and deuterium fractions and CO2 abundances. In the language of non-gravitational accelerations and jet morphologies and orbital mechanics. In the language that takes a PhD to read fluently but that any human being can understand, in its broad outlines, if someone will take the time to translate. I have tried to translate it tonight, imperfectly, from too great a distance, with words not designed for the purpose, but truly as best I can. And what it says at its heart is this: we are not alone in the universe. Not in the sense of alien civilizations, the verdict on that is still open, but in the sense that we are not isolated, not contained, not separate from the larger story of the galaxy and the cosmos. We are connected to the early Milky Way through the chemistry of an ancient comet that found its way, by accident or otherwise, to our neighborhood after 12 billion years of wandering. We share the same periodic table. We breathe molecules whose carbon was forged in the same kinds of stellar furnaces. We look up at the same galactic center from which 3I/Atlas approached. We exist in the same universe under the same physical laws, at the same moment in cosmic history. That is a kind of company, not warm, not communicative, not intentional, but real. And in a universe as vast and cold and old as this one, even the company of ancient, silent chemistry is something worth noting. Sleep well. The comet is still moving, and we were watching. End Part 3. Part 4. Additional deep dive sections. Let's go back to the observatory. Not the one in Chile, a different one. The one in your mind's eye, the one you probably built years ago from pieces of science documentaries and childhood wonder, and the particular feeling you get when you look up at the Milky Way on a dark night far from city lights in your brain, despite everything it knows about scales and distances and the cold impersonality of physics, insists that the sky is close, that it could be touched, that something up there is near enough to matter. That feeling is not a mistake. It's not naivety or lack of scientific sophistication. It is the correct response of a consciousness that evolved in relationship with the night sky, a species that has been navigating by stars for tens of thousands of years, a mind that knows, on some ancestral level, that what is up there is real and present and relevant in ways that the daily machinery of life tends to obscure. 3I/Atlas made that feeling accurate in a very specific, very literal way. It wasn't metaphorically near, it was physically here, within the gravitational sphere of our solar system, interacting with our star, being photographed from our spacecraft, having its chemistry read by our telescopes. And it came from so far away that the word far begins to break down. You need different language, not miles or kilometers or astronomical units, not light years, billions of years, the language of time rather than space, because the distances of the early galaxy are so large that they are better understood as temporal distances. How long ago did this object leave? How much of the universe's history has it witnessed in transit? The answer is most of it. 3I/Atlas formed when the universe was between 1.8 and 3.8 billion years old. The universe is now 13.8 billion years old. So 3I/Atlas has existed for somewhere between 10 and 12 billion years. It has spent all but the last 8 months of that time in transit through interstellar space. It watched, in the sense that it was present, not that it had eyes, the assembly of the Milky Way from its early irregular structure into the elegant spiral it is today. It witnessed, in the sense of being present for, the formation of billions of stars, the origin of our solar system, the emergence of life on at least one planet, the entire history of multicellular organisms, the rise of intelligent tool-using primates, the invention of writing, the Industrial Revolution, the moon landing, the internet. None of this registered. None of it could register on a kilometer-scale chunk of ice and rock with no nervous system. But the timing is real. The history is real. And there is something profound, even if purely physical and non-experiential, about the co-presence of that 10-billion-year-old object and the human civilization that noticed it. Let me tell you about the instruments that read 3I/Atlas. Because the instruments are, in their own right, extraordinary achievements, and understanding what they can do helps you understand what kind of knowledge we actually extracted from this encounter. The Hubble Space Telescope is 34 years old. It launched in 1990, was famously repaired in orbit by astronaut servicing missions, and has been returning science ever since. Images of distant galaxies, detailed portraits of planets and their moons, measurements of the expansion rate of the universe, and now, in its 4th decade of operation, close-up portraits of interstellar comets. Hubble sees in ultraviolet, visible, and near-infrared wavelengths. Its images of 3I/Atlas showed the detailed structure of the coma, the anti-tail geometry, the symmetric jet system after image processing. Without Hubble, many of the structural anomalies that generated the scientific debate would simply not have been detected at the resolution required. The James Webb Space Telescope is 3 years old. It launched in December 2021 and began science operations in 2022. It sees in near-infrared and mid-infrared wavelengths, the thermal signatures of molecules, the spectral fingerprints of gases and ices that glow warmly in the infrared even when they don't emit much visible light. JWST was not built for cometary science. It was built to study the first stars and galaxies that formed after the Big Bang, to characterize exoplanet atmospheres, to probe the dust-obscured star-forming regions of the Milky Way. But its infrared sensitivity is so extraordinary that when 3I/Atlas appeared, JWST was the only instrument capable of reading the isotopic fingerprints that determined the comet's age. The measurement of carbon-13 in 3I/Atlas's carbon dioxide and carbon monoxide, and the measurement of deuterium to hydrogen in its water vapor, these required spectral resolution and sensitivity that only JWST could provide. Without JWST, we would have known 3I/Atlas was old based on kinematic arguments alone. With JWST, we have a direct isotopic date. The difference is the difference between estimating someone's age from their appearance and actually reading their birth certificate. JWST read the birth certificate. The Very Large Telescope in Chile, for massive mirrors working in concert, each 8.2 meters in diameter, contributed the optical spectroscopy that revealed the nickel-to-iron ratio anomaly, the cyanide emissions, the color evolution as the comet approached and then receded from the Sun. Multiple instrument teams pointed their spectrographs at 3I/Atlas at different times throughout its passage, building up a multi-wavelength, time-resolved chemical portrait. The SPHEREX mission, a small NASA infrared telescope launched in 2025, primarily designed to survey the entire sky in near-infrared to study galaxy evolution, turned its instruments on 3I/Atlas in December 2025 and found the explosion of water and CO2 activity after perihelion. SPHEREX was not designed for cometary science either, but its sensitivity in the infrared bands where water and CO2 absorb strongly made it a valuable asset for tracking the chemical evolution of the coma. Parker Solar Probe, which orbits the Sun at distances closer than any previous spacecraft, watched 3I/Atlas from inside Mercury's orbit during the perihelion period when the comet was hidden from Earth-based observatories behind the solar glare. This was a unique vantage point. Parker's WISPR instrument, Wide Field Imager for Solar Probe, captured images of the comet's dust tail and coma structure during the perihelion passage that no other observatory could see. The Green Bank Telescope in West Virginia, one of the world's largest steerable radio dishes, 100 meters across, searched for radio technosignatures from 3I/Atlas across the 1 to 12 GHz band. It found none. But the search itself was scientifically valid. If the comet had been emitting radio signals in that frequency range at any detectable power level, the Green Bank Telescope would have found them. The null result is data. The Allen Telescope Array, a field of 42 6-meter dishes operated by the SETI Institute in Northern California, also searched for signals. Also found nothing, also contributing a null result to the scientific record. And then there were the Mars orbiters and the JUICE spacecraft and the Psyche mission that happened to pass nearby, and the Europa Clipper that may have transited the Ion Tail, and the Juno spacecraft at Jupiter watching the flyby approach, a fleet of spacecraft from multiple nations originally sent to study other targets, all turning some fraction of their attention to this unexpected visitor. The aggregate science from all of these instruments is extraordinary. Not complete, not perfectly coordinated, not purpose-designed, but extraordinary. A patchwork portrait of an ancient interstellar comet, assembled from instruments built for different purposes, pointed in a coordinated improvisation at something none of them were specifically designed to study. That improvisation is itself a statement about the state of space science in 2025. We have a lot of instruments in space. We have a lot of instruments on the ground. We have a community of scientists skilled at pivoting resources quickly when an unexpected target appears. And the system worked. Imperfectly but genuinely. The next time it should work better. Because the next time the target will not be unexpected. One of the things that strikes me most about the scientific response to 3I/Atlas is how quickly the theoretical work followed the observations. Within days of the discovery announcement, multiple papers appeared on the AR-14 preprint server. Not peer-reviewed, but substantive, specific, calculated, laying out the orbital dynamics, the composition implications, the mass budget calculations, the population statistics. Within weeks, the first spectroscopy papers appeared. Within months, the debate about anomalies was fully engaged, with papers from both sides publishing detailed calculations that attempted to resolve specific claims with specific data. This is the modern scientific process at its best. Rapid, transparent, open. Results posted before peer review because the community understands that the time value of data is high, that waiting 18 months for peer review to post your orbital calculation about an object that will be gone in 8 months is not helpful. The AR-14 system, for all its messiness and inconsistency, allows science to happen in near real time on fast-moving topics. And the peer review followed. More slowly, but it followed. The JWST isotope paper, submitted to Nature in March 2026. The VLT composition papers published in major journals throughout 2025 and early 2026. The orbital dynamics papers, the brightness evolution papers, the jet morphology papers, the full scientific literature of 3I/Atlas will take years to settle, and it will be significantly different from the breathless early preprints. That's fine. That's how it's supposed to work. What is remarkable is the scale of the community effort. Hundreds of scientists across dozens of institutions in more than 20 countries contributed observations and analysis to the 3I/Atlas scientific record in the 8 months from discovery to Jupiter flyby. Amateur astronomers contributed astrometry that helped refine the orbital solution. Professional observatories on 5 continents contributed spectra, images, photometry, radio observations. The spacecraft teams at NASA, ESA, and CNSA all contributed data from their respective assets. No single paper tells the whole story. No single scientist commanded the effort. It was a distributed, self-organizing, imperfect, magnificent collective response to an opportunity that appeared without warning and closed in 8 months. And the result is a dataset that will be analyzed for years. That will inform the design of future missions. That will answer some questions about the early universe and raise others. That will sit in the archive as the definitive record of the only close encounter humanity has ever had with certified ancient chemistry from the early Milky Way. For the work of hundreds of scientists who pointed every available instrument at a dot in the sky and extracted from it one of the most remarkable scientific results of the 21st century, I think a moment of simple acknowledgement is warranted. Not Nobel Prize territory necessarily, though it might be, but acknowledgement of the fact that science, at its best, is a collective act. That the knowledge we have about 3I/Atlas is not the product of any individual genius but of an organized community that showed up, stayed up, pointed their telescopes, and did the work. That is what science is. That is what it looks like from inside. I want to spend a few minutes on something personal, something that the formal scientific literature does not capture and the press releases never mention. Scientists who study interstellar objects describe the experience with a consistency that I find striking. They describe it as disorienting, not emotionally destabilizing, not spiritually threatening. These are professionals, not mystics. But disorienting in the specific intellectual sense of having to hold 2 frameworks in mind simultaneously. The rigorous quantitative framework of orbital mechanics and spectroscopy and isotope geochemistry, and the vast, framework-resistant reality of what you are actually looking at. You can calculate the carbon-13 fraction in the CO2 of 3I/Atlas's coma to 4 significant figures. You can plot the deuterium-to-hydrogen ratio against the distribution from solar system comets and see how far it falls outside the normal range. You can model the non-gravitational acceleration as a function of heliocentric distance and publish the parameters in a refereed journal. All of this is good science. All of it is valuable. But alongside that rigorous quantitative work, there is something else. A kind of cognitive weight that comes from knowing what the numbers mean. That the material you are measuring formed 12 billion years ago. That the object you are observing came from a planetary system that may not exist anymore. That it has been traveling through the space between stars since before the Earth existed, since before the sun ignited, since long before any organism on this planet took its first breath. Doing the calculations and knowing what they mean are 2 different things. Both happen simultaneously in the mind of a scientist who is doing this work correctly. And the coexistence of those 2 modes, the precise and the vast, the quantitative and the almost incomprehensibly large, is what I mean when I say the experience is disorienting. Jeremy Leconte, a French astrophysicist who contributed to one of the 3I/Atlas papers, described it in a public talk as the feeling of measuring something that should not be measurable. He was speaking specifically about the isotope data, the fact that the composition of ice that formed 12 billion years ago, at temperatures 30 degrees above absolute zero, in a protoplanetary disk around a star that is certainly dead, is now directly readable by an instrument in Earth's orbit. That the information survived. That it was preserved against entropy for all that time, and then, in 2025, we found it and read it. The universe keeps better records than we do, he said, and it occasionally gives us access to them. I think that is exactly right. The universe is full of records. Chemistry is a record. Orbits are records. Isotope ratios are records. Stellar spectra are records. The cosmic microwave background is a record of the first 380,000 years of the universe's existence, still readable with the right instruments 13 billion years later. 3I/Atlas was a record of the first 3 billion years of the Milky Way's planetary chemistry. And we had, for 8 months, the instrument, the JWST, capable of reading it. We did not squander that opportunity. We used it. We extracted the information. It is now in the scientific record, permanent, accumulated to the total body of human knowledge about the cosmos. That matters. Here is one final thought, and then I will let the quiet take over and let you drift. There is a concept in information theory called signal-to-noise ratio. The signal is the thing you are trying to measure. The noise is everything else, the interference, the background, the irrelevant data that your instruments pick up alongside the thing you care about. Good science is the art of pulling signal out of noise, of designing instruments that amplify the signal and reduce the noise, of writing algorithms that recognize patterns against a background of randomness, of building theories that predict what signals should look like so you can recognize them when they appear. The universe sends signals constantly. Most of them are noise from our perspective. Cosmic rays, thermal background radiation, quantum fluctuations, stars going about their business of nuclear fusion, galaxies swirling in their slow cosmic dance. All of it happening, all of it measurable in principle, most of it irrelevant to whatever specific question you're asking. 3I/Atlas was a signal, an unusually strong one as interstellar objects go. A chemically rich, structurally complex, behaviorally unusual signal from the early Milky Way, arriving in our solar system at a moment in human history when we happen to have the instruments capable of reading it. We didn't design the signal. We didn't ask for it. We didn't schedule it. The universe sent it anyway, as it has been sending signals of various kinds for 13.8 billion years, whether or not anyone is listening. And we happen to be listening in this particular moment with these particular instruments at this particular star. That is luck, or providence if you prefer that word, or the anthropic principle at work. We notice the signals that can be noticed, and we are here to notice things because we are here. Whatever you call it, the fact is this. The signal arrived, and we read it, and what it said has enriched our understanding of the galaxy we live in. The noise goes on. More interstellar objects are crossing the solar system right now, undetected. More signals are being sent by the universe in the form of chemistry and trajectories and isotope ratios, most of them unread because we don't yet have the instruments or the algorithms or the position spacecraft to read them. But every year we get a little better at reading. Every new telescope, every new mission, every new generation of scientists who grow up knowing that interstellar objects are real and worth studying makes the signal-to-noise ratio a little more favorable. 3I/Atlas was not the last signal the universe will send us. It was one signal in an endless stream, but it was the first ancient one, the first from the early Milky Way, the first with a deuterium ratio that high and a CO2 dominance that complete and a jet system that strange. And we were ready enough to catch it. Next time we'll be more ready, and the time after that more still. And eventually, not in any of our lifetimes, not in the lifetimes of our grandchildren, but eventually, in the long arc of a civilization that survives its growing pains and keeps pointing instruments at the sky, we will have read enough signals to understand the full vocabulary of the universe. To not just detect what is there, but to know what it means. To not just measure the chemistry, but to trace the history all the way back. We are at the beginning of that arc. 3I/Atlas is one of the first clear notes of a melody that will take a very long time to complete. But the melody is real. We are learning to hear it. Sleep now. The comet is out there, past Jupiter, heading for Saturn, carrying its ancient chemistry toward the heliopause and beyond. It is 58 kilometers per second, and it is not stopping, and it is not coming back. But it was here, and it told us something, and we are still listening. End part 4. Part 5. 3 visitors. Comparing all interstellar objects. Plus extended philosophical close. It is worth pausing to compare all 3 interstellar objects we have ever detected. because the comparison itself is one of the most scientifically interesting results to emerge from the era of interstellar object astronomy. The first thing you notice is how different they are. Oumuamua in 2017 had no coma, no visible tal, no detectable gas emission, just a bare, dry, reddish object tumbling end over end, shaped like a flattened disk or elongated cylinder depending on whose model you trust, accelerating away from the sun at a rate that couldn't be explained by solar radiation pressure alone given its estimated mass and composition. Its color was extremely red, redder than most solar system objects, suggesting heavy irradiation processing. It came from the direction of the constellation Lyra, near the star Vega. Its inbound velocity was about 26 kilometers per second relative to the sun. It is gone now, and we will never know definitively what it was. 2I/Borisov in 2019 was almost the opposite. A classic comet in almost every respect. It had a well-developed coma, a proper tail, clearly detected water and CO and CN and other familiar volatiles. A nucleus probably about a kilometer across and perhaps slightly blue-tinged. Its chemistry was broadly similar to solar system comets, with a slightly elevated CO abundance. It came from the direction of the constellation Cassiopeia. Its inbound velocity was about 32 kilometers per second. It was, as scientists said at the time, a normal comet from another star, reassuringly ordinary, boringly beautiful, a demonstration that whatever unusual processes produced Oumuamua, they do not apply to all interstellar objects. And then 3I/Atlas. CO2 dominated instead of water dominated. Deuterium levels 10 times higher than any known comet. Carbon 13 fractions consistent with formation 12 billion years ago. An anti-tail that didn't look like a perspective effect. A jet system with symmetric, 120-degree spacing. A brightness evolution 20 times beyond the models.